NASA reached the edge of the Sun's empire, and the solar system didn't end. The instruments saw a boundary that flexed, leaked and folded, less like a wall in space, more like a seam in reality. So what did we actually hit out there? And what terrifying absence did NASA discover that forces us to rethink our place in the universe? Out beyond the last planet, a human-made signal is still whispering, proof that our map of home was never finished. NASA went looking for an edge, and the edge refused to behave like an edge. In the deepest wide shots, the solar system looks complete. Planets in their lanes, darkness beyond, and the sun's authority fading to nothing. For decades, NASA drew that ending as a clean border, a place where the solar wind stops and the galaxy begins. But far past Neptune, where radio commands take hours to arrive, the instruments began sending back a different kind of story, one written in particles, fields, and missing signatures. This documentary begins with a simple question and a dangerous assumption. What did NASA actually discover at the edge of the solar system? And why does what they didn't find there force us to rethink what outside even means? Because the sun does not merely shine, it breathes, an invisible wind of charged plasma carrying magnetism into space. That wind carves a vast bubble around every orbit we know, a living region that expands, compresses and shudders with solar storms that arrive years late. Textbooks promised a sequence you could diagram, a shock, a sheath, then a boundary that reads like a line. Yet the farther our probes travelled, the less the frontier resembled a wall. The data hinted at an outer realm that is not empty, not quiet, and not obligated to match our geometry. One detector would declare a crossing while another hesitated. One curve would rise as another refused to turn. Even the silence, the signatures that should have appeared and did not, became part of the evidence. Two spacecraft, launched in the 1970s for planetary flybys, became accidental witnesses to the most elusive border we have ever tried to touch. Their power is fading, their instruments aging, and still their telemetry arrives. Patient, narrow, and unforgiving. Each number is a clue, and each clue asks the same question. Are we approaching an ending, or an interface? To answer it, we will rebuild the frontier from the ground up, first in objects and orbits, then in forces you cannot see. We will follow the solar wind as it slows, heats, and tangles, and we will watch the galaxy press back with its own pressure and magnetic order. Then we will widen our viewpoint beyond a single trajectory, using a mission that can image the boundary indirectly, turning sparse counts into an all-sky portrait. And as the picture grows, the stakes grow with it. Because the edge of our solar system is not just a distant location, it is the first place where the sun negotiates with the Milky Way on equal terms. If that negotiation is messy, layered and shifting, then our oldest categories, inside and outside, home and interstellar, boundary and beyond, are not laws of nature. They are approximations. What NASA found at that frontier is more than a destination. It is a lesson in how the universe draws borders, rarely as lines, often as zones, and sometimes as seams. Tonight we follow the faintest signals we have ever trusted, into the dark where definitions start to fail. And along the way, we will confront a final, unsettling possibility, that the most important discovery is not the thing out there, but the absence of the simplicity we expected to find. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now settle in for a journey. We begin with a map that should have had an edge, then push outward through shocks, ribbons and interstellar weather. By the time we reach the farthest crossings, the frontier will look less like a wall and more like a measurable mystery. The spacecraft is far beyond the last planet, still listening, still reporting, still refusing to end the story. Its signal is faint but steady, a narrow carrier wave stretched thin by distance, yet it keeps arriving minute after minute. On Earth, giant antennas tilt and track, pulling meaning from a whisper buried in cosmic static. The numbers that emerge do not match the clean boundary drawn in textbooks, and that mismatch is the first tremor of a larger revelation. Engineers expected an edge that behaved like a border, a crisp change you could plot on a chart. Instead, they received evidence of a frontier that behaves like a puzzle, with answers that depend on how you ask. For decades, NASA built a map of our cosmic home with an assumption baked in, because assumptions are how exploration begins. The sun blows a wind of charged particles, mostly protons and electrons, and that wind should carve a protective bubble in the surrounding galaxy. In the simplest view, the solar wind expands supersonically, cools as it spreads, and carries the sun's magnetic field outward like a spiraling ribbon. That bubble should thin smoothly, then yield to the galaxy's pressure at a definable line. The farther we travelled, the more certain that line seemed, because the models looked elegant and the math behaved. Then the data started arguing back, quietly at first, then with accumulating insistence. The mystery is not only what was found at the edge, where the sun's reach should finally weaken. The deeper shock is what was missing where it should have been, like a landmark that never appears on the horizon. A predicted structure did not appear in the expected form, even though the physics behind it seemed straightforward. Several measurements refused to line up with the simplest models, and the disagreement was not a rounding error. The boundary was not where it was supposed to be, and it did not behave like a simple shell. It behaved like a living interface, shifting under forces that do not announce themselves. When people say edge of the solar system, they usually mean a place. NASA learned it is also a definition. The solar system has multiple borders stacked like layers, each one real in a different way, and each one shaped by a different kind of evidence. Some edges are made of rocks and ice, counted by telescopes and inferred from orbital dynamics. Another edge is made of fields, plasma and pressure, sensed only by instruments that can taste the invisible. The word edge sounds singular, but the reality is plural, an architecture of thresholds. Start with the region beyond Neptune, where sunlight is weak and the clock of orbit slows down. Out there, the sun is not a blazing disk but a hard, bright star, and its warmth becomes a memory rather than a presence. The Kuiper Belt is a broad ring of icy bodies, the source of many short-period comets, and it is also a fossil record of early chaos. These objects preserve volatile ices and primitive chemistry, materials that were never fully cooked by the inner solar system. It is not a wall. It is a population, a distribution, a record of how planets formed and migrated, leaving debris in resonant patterns like ripples frozen in time. Historically, this region was not always part of the public map, because for most of human history it could not be. The idea of a belt beyond Neptune grew from theory, from the need to explain comet origins and the leftover building blocks of planets. When the first Kuiper Belt objects were confirmed in the 1990s, the solar system's outline expanded overnight, and the old picture began to look incomplete. Even now, surveys reveal new bodies and new substructures, and each discovery reminds us how much darkness still hides. The outer solar system is not empty space. It is a thinly populated museum, and its exhibits move. Beyond that sits the scattered disk, where objects follow stretched, tilted paths shaped by Neptune's gravity. Some are thrown outward, some are pulled inward, and many remain in unstable compromise, slowly evolving over millions of years. Their orbits are signatures of gravitational encounters, like fingerprints left by a planet that never stops stirring. This region already breaks the idea of a neat perimeter, because the objects do not respect a circular boundary. The solar system's architecture is messy because its history was violent, and because gravity is patient enough to keep rearranging the aftermath. Farther out, the Oort cloud is inferred rather than seen directly, a vast reservoir of icy remnants bound loosely to the sun. Its existence is suggested by the arrival directions of long-period comets, which fall inward as if released from a distant sphere. If it exists as predicted, it extends a significant fraction of the distance to the nearest stars, where the sun's grip becomes a gentle suggestion. That makes the solar system enormous by one definition, and it makes the word edge feel almost meaningless. What is an edge when the boundary is a thinning probability, not a fence? Yet NASA's most urgent edge was never about the last piece of ice. It was about the sun's influence as a physical environment, the space weather domain that wraps every planet. The solar wind expands outward, carrying the sun's magnetic field into space, and that field is embedded in the plasma like threads in flowing fabric. It pushes against the interstellar medium, the thin gas and magnetic field between stars, which is itself moving and structured. Where those pressures balance, the heliosphere should end, at least in the cleanest version of the story. This is not a metaphorical border. It is a contest of momentum, magnetic tension, and particle energy. This is the edge that matters for our daily reality, even if it is unimaginably far away. The heliosphere helps shield the planets from a portion of galactic cosmic rays, energetic particles accelerated by distant astrophysical violence. It shapes how energetic particles reach Earth and how radiation behaves across the solar system, influencing spacecraft electronics and astronaut risk. It is also a laboratory for plasma physics that cannot be built on Earth, because no vacuum chamber can reproduce a boundary measured in billions of kilometers. Out there, nature runs the experiment continuously, and our probes are the sensors. NASA expected the heliosphere to look like a bubble moving through a calm sea, with the sun's wind pushing outward in all directions. The solar wind should slow down at a termination shock, where it transitions from supersonic to subsonic flow as it begins to feel the galaxy's resistance. Past that should lie a turbulent region called the heliosheath, where plasma is heated, compressed, and stirred by instabilities. Farther still, the heliopause should mark the boundary where solar plasma yields to interstellar plasma, a contact surface between two different regimes. The transition should show recognizable signatures in particle populations and magnetic behavior, like a change in accent that signals a new country. The simplest picture predicted smooth gradients and predictable changes, because symmetry is an attractive assumption. The solar wind should weaken in an orderly way, its density dropping with distance, and its speed changing in a measured progression. The magnetic field should rotate in a clear pattern as the spacecraft crossed into interstellar space, reflecting a shift from the Sun's spiral field to the galaxy's local field direction. The external pressure should balance the internal pressure at a stable distance, producing a boundary that is roughly symmetric, perhaps slightly squashed by motion. In that expectation, the heliosphere was an object you could draw cleanly, like a sphere, or a teardrop, or a comet-shaped ball. Then the farthest explorers arrived at the place where the map said the edge should be. The instruments did not report a clean ending, and they did not agree on a single moment of departure. They reported discontinuities, unexpected turbulence, and asymmetries that suggested the boundary was distorted by forces we had underestimated. They reported a frontier that looked less like a circle and more like a shape under stress, as if the bubble were being pressed, wrinkled, and tugged. The data felt like a coastline seen through fog, where the line keeps moving as you approach. One surprise was timing, because timing is distance turned into expectation. The boundary was not located where many models placed it, and it did not appear at the same distance in different directions, implying a lopsided heliosphere. That asymmetry hints at an interstellar medium with its own gradients, flows, and magnetic pressures that are not uniform. Another surprise was behavior. Instead of a single simple crossing, the data implied a complex region with changing conditions, as if the spacecraft was skimming along folds. The edge acted like a dynamic interface, not a static wall, and the sun's influence did not switch off like a light. NASA also expected certain particle signatures to behave in a straightforward way, because particles are often the most honest witnesses. Inside the heliosphere, solar particles dominate, including the solar wind and populations shaped by solar activity. Outside, galactic cosmic rays should rise as the sun's shielding falls away, because the heliosphere acts like a modulator. That overall trend appeared, but the details were not tidy, and the transition did not look like a simple ramp. The changes were sharper in some measurements and strangely gradual in others, suggesting layered transport and magnetic barriers. It was as if the boundary had texture, with channels and pockets rather than a single surface. The magnetic field was supposed to offer a decisive clue, because magnetism can mark ownership of space. A clean boundary should show a clear shift from the sun's magnetic influence to the galaxy's, with a noticeable change in field direction and behavior. But the field did not behave like a simple handoff, and it refused to provide the satisfying signature the models promised. Some readings suggested continuity where a break was expected, as if the field lines were draped and aligned rather than replaced. Other readings suggested abrupt changes without the clean rotation that many anticipated, implying reconnection, turbulence, or geometry we did not predict. The result was a contradiction that felt almost philosophical, because it challenged the categories we rely on. The spacecraft seemed to be outside by one definition, and still connected by another, depending on whether you trusted particles, fields, or plasma waves. It was as if the border was both real and ambiguous, a boundary that existed but could not be summarized by a single measurement. NASA had not reached a line. NASA had reached a zone. In that zone, the universe reminded us that definitions are tools, not truths. This is where the chapter's emotional premise locks into place, and the tone turns from travelogue to interrogation. These probes are not only travelling through distance, they're testing the assumptions we use to draw reality into categories, and they are doing it with unforgiving precision. We want edges to be definite because they make the universe feel legible, and because legibility is a kind of comfort. The Heliosphere refused to cooperate with that need, and the refusal was not dramatic. It was methodical, delivered as telemetry. The unsettling discovery is not a monster at the boundary. It is the absence of the expected simplicity, the missing clean geometry that would have made the story easy to tell. The missing structure is a missing certainty, a missing agreement between models and measurements, a missing moment you can point to and say, there. In that gap, the story begins because science advances fastest when the map fails. What does it mean when the best instruments we can send return answers that do not fit our questions? Because the heliosphere is not only a local bubble, it is a contact surface between the Sun and the galaxy, and contact surfaces are rarely smooth in plasma physics. Its shape depends on the interstellar medium's density, temperature, flow, and magnetic field, and those properties can vary across surprisingly small scales. If the boundary is asymmetric or unstable, that implies the galaxy's environment is not what we assumed, at least not in our neighbourhood. It implies our local interstellar cloud is more structured, more pressurized, and more dynamic than the simplified backdrop in older diagrams. The Sun is not sailing through still water, it is moving through weather. That matters because cosmic rays are not just a hazard. They are a tracer of astrophysical processes across the Milky Way, and their energies encode the history of their acceleration and scattering. They carry information about supernova remnants, magnetic turbulence, and the large-scale circulation of energy, even when their paths are scrambled. The heliosphere filters them, bending trajectories and changing intensities, so understanding the filter changes what we think we're measuring. If the filter has folds and leaks, then the cosmic ray picture at Earth is not a direct window. It is a view through glass with subtle distortions. It also matters because the heliosphere sits inside a larger chain of boundaries, and boundaries evolve. The Sun moves through interstellar clouds over time, and the heliosphere's size and shielding can change as external density and magnetic pressure change. Earth's radiation environment can shift on geological timescales, not as a sudden apocalypse but as a slow alteration of background conditions. The edge is not a fixed landmark. It is a moving relationship, a negotiation that depends on where the Sun is in the galaxy. When we talk about a stable space climate, we may be describing only a temporary era. NASA's measurements force a question that sounds small but expands quickly. If our local boundary is more complex than predicted, what else have we simplified too aggressively? If the interface between solar plasma and interstellar plasma is messy, what does that say about other cosmic interfaces, from planetary magnetospheres to the edges of stellar winds? The universe is full of seams. Some seams are quiet and some are violent, but all of them test the limits of our categories. When a seam refuses to behave, it becomes a clue. This documentary follows that seam outward and backward. We begin with the outer architecture of the solar system, where debris fields record ancient migrations and resonances preserve the memory of moving planets. We move to the heliosphere, where plasma and magnetism rewrite the idea of a border, and where outside becomes a question of diagnostics. Then we step into the interstellar medium itself, where the Sun is only one actor in a larger flow, embedded in a galactic environment with its own fields and turbulence. The story is not about reaching the end. It is about learning what end even means. From there, the story connects to the oldest light in the universe, the cosmic microwave background that fills all space. That light is measured through foregrounds and filters, including the heliosphere's influence on particles and fields near our instruments. Local boundary physics can leak into cosmological interpretation, not by rewriting the cosmos, but by biasing what we think we see. The edge of the solar system can quietly touch the edge of what we think we know, which is why this frontier matters beyond its distance. When the nearest boundary is complicated, even the farthest conclusions deserve a second look. The central question is simple to ask and hard to answer. What did NASA actually discover at the edge of the solar system? Why did what they did not find there matter as much as what they did? And how can a missing expected structure force us to rethink our place in the universe? The drama is not in an explosion. The drama is in a discrepancy that refuses to go away. The map we drew assumed an ending. The data suggested a transition, a negotiation, a boundary that breathes and bends as conditions change. The farther we go, the less the border looks like a line, and the more it looks like a region with thickness. It looks like a place where competing pressures write temporary rules, and where stability is an approximation. If the heliosphere is a shield, it is a shield with edges that fray. In the next chapter, we start building the solar system outward, piece by piece, to see what an edge even means. We follow the debris, the orbits, and the gravitational leftovers that set the stage for the Sun's final frontier. And as the architecture takes shape, one question will keep returning. What happens when the universe refuses to draw straight lines for us? Chapter 1 left us with a problem disguised as a destination. NASA went looking for an edge and found a seam. To understand why that seam matters, we rebuild the solar system outward like a detective. We start with what we can count, then follow what we can only infer. The planets are not the whole solar system. They are the brightest evidence in a much larger gravitational case file, luminous suspects surrounded by quieter accomplices. In wide shots, the inner planets look like a tidy clockwork. In reality, the solar system is a gradient of debris, where distance dims light and certainty at the same time. Beyond Neptune, the Kuiper Belt begins as a broad, cold population of icy bodies. These objects are small, dark and numerous, and they preserve early solar system material. Visually, it is less a ring than a haze, tiny worlds scattered across a black ocean, each reflecting only a few photons back to Earth. Their surfaces are cold enough for volatiles to survive, which is why they function like deep freeze archives. We have actually observed thousands of Kuiper Belt objects through deep surveys. We measure their brightness, estimate sizes, and correct for what we miss. Those measurements are indirect because brightness depends on both size and reflectivity. A small, bright object can masquerade as a larger, darker one, so astronomers fold in assumptions about albedo to translate light into kilometers. Those corrections are not cosmetic. They are the difference between a sparse ring and a massive reservoir of leftover building blocks. Survey teams map detection efficiency like a weather forecast, how likely a moving point of light is to be found against starfields and instrumental noise. The farther out we look, the more the census becomes a probability statement rather than a head count. The Kuiper Belt is structured, and structure implies history. Orbits cluster into families that do not happen by accident. If you could draw those orbits as glowing threads, you would see bands and gaps, inclinations fanning upward, and eccentricities stretching paths into subtle ovals. That geometry is a fossil, because gravity writes in patterns and rarely erases them completely. One family sits in orbital resonances with Neptune. Pluto is the famous example, locked into a stable rhythm that prevents close encounters. Pluto's 3-2 resonance means it completes 2 orbits for every 3 of Neptune's, meeting the giant planet only when geometry keeps them safely separated. The resonance is not a coincidence, it is an agreement enforced by repeated gravitational tugs. Resonances act like gravitational traps. They capture objects during slow changes in Neptune's orbit, then hold them for billions of years. In dynamical terms, resonant angles librate rather than circulate, which is a technical way of saying the orbit rocks around a stable configuration. That rocking motion is the signature we read, because it survives long after the migration that created it. That capture is a signature of migration. Neptune did not form exactly where it is now, and the belt remembers the move. Early in solar system history, the giant planets interacted with a disk of planetesimals, exchanging angular momentum in countless small encounters. Neptune tended to move outward as it scattered bodies inward, and Jupiter tended to move slightly inward as it ejected bodies outward. Models of planetary migration predict specific resonance populations. The observed ratios between resonant groups test those models against reality. A smooth, gradual migration sweeps resonances like a slow-moving net, capturing objects efficiently in certain locations. A more chaotic migration, punctuated by jumps, leaves different fingerprints, including emptier resonances and dynamically hotter survivors. The belt also shows a sharp outer edge in many surveys, near a few dozen astronomical units. That drop-off could reflect formation limits or later sculpting. In images, that edge is not a wall but a sudden thinning, like fog that abruptly clears. It could mark where the primordial disk became too sparse for large bodies to assemble, or where later dynamics removed objects and left a truncated population. Size distributions add another clue. There are many small bodies, fewer large ones, and a break that hints at collisional grinding. That break matters because it separates two regimes of history. Above the break, objects may preserve original growth outcomes, while below it, repeated impacts may have shattered and reprocessed the population into fragments. We infer that breaks statistically, because telescopes see only a biased slice. The faintest objects vanish into noise long before they vanish from space. A survey's limiting magnitude sets an invisible horizon, and beyond it, the Kuiper belt becomes a shadow population. Astronomers correct by modelling how many objects should exist just below detectability, then extrapolating with carefully tested power laws. Occultations offer a different method. When a tiny body passes in front of a star, it reveals itself by a brief, precise dimming. The visual is almost unfairly subtle. One star in a crowded field blinks for a fraction of a second, then returns as if nothing happened. Yet that blink encodes size, distance, and sometimes even hints of shape, because diffraction and timing leave telltale patterns. Occultation results suggest abundant sub-kilometre objects, but the uncertainties remain large. Even so, they constrain how much mass hides below detection. Those uncertainties come from rarity and geometry, because occultations require alignment across billions of kilometres. Still, even a handful of events can rule out extreme models, which is powerful when direct imaging cannot reach those sizes. The Kuiper belt is not a single ring. It includes cold, classical objects with low inclinations and hotter populations with tilted, excited orbits. That dynamical temperature matters. Cold orbits suggest gentle preservation, while hot orbits suggest past stirring by planets and resonances. Cold classicals often show distinctive colours and a higher fraction of fragile binaries, which supports the idea that they formed and remained in a relatively quiet zone. Hot populations, by contrast, look like immigrants, objects displaced, tilted and stretched by earlier gravitational turbulence. Some Kuiper belt objects are binaries, paired bodies orbiting each other at wide separations. Their survival implies low collision speeds in parts of the belt. A wide binary is a delicate system, because a strong impact or close gravitational encounter can unbind it. When we find such pairs still intact, we are seeing evidence that certain regions avoided violent stirring, an environmental clue written in orbital companionship. Even chemistry becomes evidence. Surface colours and volatile retention vary with distance and history, hinting at where objects formed and how they moved. Methane, nitrogen, and carbon monoxide ices can persist on the coldest, largest bodies, while smaller objects lose volatiles and develop radiation-processed crusts. Over time, solar ultraviolet light and cosmic rays redden surfaces, turning some worlds into dark, rust-coloured embers. At this stage, the solar system's edge still looks like objects on a map, but the map already refuses to be clean. Beyond the belt sits a population that breaks the idea of a circular boundary. The scattered disk is defined by elongated, unstable orbits. Scattered disk objects approach Neptune at perihelion and swing far outward at aphelion. Their paths look like the aftermath of close gravitational encounters. If you animate their motion, they behave like thrown stones, rushing inward, slingshotting past Neptune's neighbourhood, then coasting outward into darkness. Each pass is a chance for Neptune to change their energy slightly, and over many encounters small changes accumulate. This is evidence of dynamical upheaval. Neptune's gravity can kick bodies outward, and repeated encounters can stretch orbits over time. Gravitational scattering is not random chaos, because it follows conservation laws, but it feels chaotic in outcome. Tiny differences in encounter geometry can decide whether an object is gently nudged, flung into a long ellipse, or ejected from the solar system entirely. Some objects become detached, with perihelia lifted away from Neptune. Their detachment implies additional mechanisms beyond simple scattering. Possible mechanisms include resonance interactions during migration, encounters with massive planetesimals, or perturbations from passing stars early on. Resonances can temporarily protect an object while its perihelion is raised, then release it into a safer orbit that no longer crosses Neptune's reach. A passing star, even at a distance, can also torque distant orbits. Subtle, but decisive when the Sun's grip is weak. Sedna and similar bodies sharpen the mystery. Their perihelia are too distant for Neptune alone to explain, yet they remain bound to the Sun. Sedna's orbit is a long, slow loop that keeps it far beyond Neptune even at closest approach. It is a reminder that the outer solar system contains objects whose histories may include influences we do not see anymore, events that left no monument except the orbit itself. These extreme orbits suggest that the early solar system did not evolve in isolation. It likely formed in a stellar neighbourhood where encounters were plausible. Young stars are born in clusters, and clusters are crowded compared with today's solar neighbourhood. In that early environment, another star could pass close enough to reshape the outskirts, while the gas and dust of the natal cloud still lingered in the background. Population models estimate how many scattered and detached objects exist. Those models depend on survey biases, orbit fitting, and assumed size distributions. Orbit fitting itself is a patience game, because distant objects move slowly against the background stars. A short observational arc can mimic multiple possible orbits, so astronomers return year after year until the uncertainty collapses into a reliable trajectory. The uncertainties are part of the story. At the outskirts, the solar system is measured through statistics, not complete inventories. Still, the scattered disk tells us something firm. The outer solar system was shaped by migration, scattering, and long-term gravitational diffusion. This is where the detective reconstruction gains momentum. We are not just listing regions, we are reading the forces that built them. Short-period comets provide another line of evidence. Many of them match Kuiper belt and scattered disk source pathways when integrated backward. When we run their orbits in reverse through numerical simulations, the comets trace corridors shaped by Jupiter and Neptune. The details vary, but the overall picture is consistent. These comets are not visitors from nowhere. They are leakages from known reservoirs. Their lifetimes are short on cosmic timescales. That means the source reservoirs must continuously resupply them, or the comets would be gone. Comets fade because they lose volatiles, fracture under thermal stress, and sometimes break apart after repeated passes near the Sun. Each return is a little act of erosion, and the population would drain quickly without a distant storehouse feeding it. Now the scale expands again, from tens of astronomical units to tens of thousands. The next region is mostly invisible, yet it explains what we see. The Oort cloud is a hypothesis built from long-period comets. These comets arrive from far away on orbits with enormous semi-major axes. Their inclinations are nearly isotropic. They do not prefer the plane where planets orbit, which argues for a roughly spherical reservoir. That isotropy is a geometric clue, because disks produce disks. But repeated distant perturbations can randomize directions. A spherical cloud implies a history of scattering outward, followed by slow reshaping under external gravitational fields. Jan Oort proposed that reservoir to explain the distribution of comet energies. A distant cloud makes the observed near-parabolic orbits natural. In 1950, Oort noticed that many comets arrive with energies suggesting they are only weakly bound to the Sun. If they had been repeatedly visiting the inner solar system, planetary encounters would have altered that distribution more dramatically. So he inferred a vast, distant source. We cannot image the Oort cloud directly with current technology. Its objects are too small, too cold, and too far to reflect enough light. At those distances, sunlight is a feeble glow, and even large objects would be dimmer than the limits of most surveys. The cloud is therefore a theoretical landscape, built from trajectories rather than photographs. So we infer it from trajectories. We measure comet orbits precisely, then ask what source distribution can produce them. The key is the original orbit before planetary perturbations. When a comet enters the inner solar system, planets rewrite its path. Jupiter is especially influential because its mass makes it a gravitational editor, adding or subtracting orbital energy with a single close pass. That is why astronomers compute original orbits by removing planetary effects and estimating what the comet looked like before it crossed the giant planets. By reconstructing pre-encounter orbits, we estimate how tightly bound the comet was to the Sun. Many appear barely bound at all. That barely bound state is a clue. It implies a reservoir where the Sun's gravity is weak and external nudges can send bodies inward. Those nudges come from galactic tides and passing stars. Over millions of years, small perturbations change perihelia and inject comets toward the planets. The galactic tide is a slow, persistent pull from the Milky Way's mass distribution, gently flexing distant orbits like a hand bending a long spring. Passing stars add sporadic kicks, and even distant encounters can matter when orbital periods span millions of years. The Oort cloud also implies an early scattering phase. giant planets likely ejected vast numbers of icy bodies, and some were captured into distant orbits. Most scattered bodies would have been lost to interstellar space, which is why the cloud is thought to be a small fraction of the original debris. The fact that any were retained suggests a delicate balance between ejection and stabilization. Capture requires energy exchange. In a dense birth cluster, stellar encounters can lift perihelia and circularize distant orbits, enough to keep them bound. In plain terms, the Sun needed help holding onto what it flung outward. A nearby star can alter an orbit just enough to prevent a returning body from being thrown away permanently by the giant planets. That connects the edge to the beginning. The Oort cloud is a fossil of the Sun's early environment, not just a faraway storage bin. If the cloud exists as predicted, it extends a significant fraction of the distance to nearby stars. That makes the solar system enormous by one definition, but definitions are the trap Chapter 1 warned us about. The word edge can mean at least 3 different frontiers. One edge is gravitational. The Sun's gravity technically extends forever, but its practical dominance fades against the galaxy's field and nearby stars. We can define a sphere of influence where solar orbits remain stable over long times. Beyond that, the galaxy becomes the main architect. That stability is not just about distance, it is about time scale. Whether an orbit remains recognizably solar over billions of years. Far enough out, a small stellar encounter can rewrite an orbit more effectively than the Sun can preserve it. Another edge is material. That is where the density of solar system bodies drops, and the reservoirs thin into statistical guesses. In that sense, the edge is a signal-to-noise problem as much as a physical boundary. Objects still exist, but they become too sparse to map cleanly, and our knowledge becomes a contour line drawn from incomplete data. A third edge is physical environment. That is where the Sun's plasma and magnetic influence yield to the interstellar medium. This is the edge spacecraft can feel, because plasma has pressure, magnetic fields have direction, and particles carry energy that instruments can count. It is an interface you can cross and immediately notice, even if nothing looks different to the eye. These edges do not coincide. The outer architecture of objects can extend far beyond the boundary of the Sun's wind. That mismatch is the pivot. The frontier NASA can measure directly is not the last comet, but the last breath of solar plasma. Before we reach that pivot, we need to be clear about how inference works at the outskirts. We do not just discover objects, we reconstruct populations. Orbital distributions are the first tool. The clustering of semi-major axes, inclinations and resonances encodes the forces that shaped them. Those distributions act like a statistical fingerprint, because gravity produces characteristic patterns under migration and scattering. When we see a resonance overpopulated or an inclination distribution unusually hot, we are seeing the aftermath of a specific kind of history. Comet trajectories are the second tool. They act like test particles released from distant reservoirs, tracing pathways back to their sources. A single comet is anecdotal, but thousands become a dataset, and the dataset reveals injection mechanisms, which comets arrive from which directions, and with what energies becomes a map of the invisible. Occultations are the third tool. They detect bodies too faint for imaging, turning starlight into a ruler for hidden size ranges. In practice, this means watching many stars at high cadence and waiting for rare, sharp dips. The method is unforgiving, but it reaches into a regime where traditional telescopes are blind. Statistical population models are the fourth tool. They combine survey limits, detection efficiencies, and dynamical simulations to estimate what remains unseen. These models are where observation meets computation, and where assumptions matter most. Albedo distributions, size slopes, and orbital priors can shift the inferred mass by orders of magnitude. That sensitivity is why competing models can coexist for years. Each tool has failure modes. Survey biases favor brighter objects, orbit fits can be uncertain, and dynamical histories can be degenerate. Degeneracy means different pasts can produce similar present-day distributions. That is why the outskirts are both a record and a riddle. Neptune's migration is a central example. A smooth migration captures resonant populations differently than a chaotic, jumping migration. The observed belt suggests a migration history that was not perfectly smooth. Some features hint at instability, scattering, and reorganization among the giant planets. Even the cold classical population, which looks comparatively undisturbed, becomes a constraint. If migration were too violent, that fragile structure might not have survived. The belt therefore acts like a seismograph, recording how hard the early solar system shook. That connects to broader models like the Nice framework. In those models, giant planets rearrange, resonances sweep, and small bodies are redistributed. The scattered disk becomes the debris field of that event. The Kuiper belt becomes the preserved structure that survived it. The Oort cloud becomes the distant echo populated by bodies flung outward and then stabilized by the galaxy's gentle pull. So the solar system's outer architecture is not a boundary line. It is a layered set of populations, each shaped by gravity over deep time. Yet gravity is not the only influence that matters for NASA's Edge story. The spacecraft were not built to count every distant object. They were built to measure fields, particles, and pressure. Their most decisive frontier is the heliosphere, because it is a physical interface. The sun emits a continuous solar wind. It carries plasma outward and drags the solar magnetic field into a spiral through rotation. That spiral, often called the Parker spiral, forms because the wind streams outward while the sun turns beneath it. The result is a magnetic field that is not radial like spokes, but curved like a rotating sprinkler's spray. That wind creates a bubble in the interstellar medium. The bubble's size depends on solar wind pressure and the external galactic environment. Pressure here is literal, because charged particles exert force as they stream, collide, and gyrate around magnetic fields. When the outward push of the solar wind weakens with distance, the surrounding interstellar plasma and magnetic field begin to push back. The heliosphere is not defined by where objects orbit. It is defined by where solar plasma stops dominating local space. This is where the meaning of Edge becomes operational. Instruments can detect particle populations, magnetic fields, and plasma waves in real time. At large distances, the sun's gravity still holds comets, but the sun's wind can be stopped, compressed, and redirected by the galaxy. So the story shifts from inventory to interaction. The question becomes not what is out there, but what the boundary does. The outer architecture sets the stage for that boundary. It tells us the solar system's history was messy, and messy histories produce complex frontiers. If the Kuiper belt is structured by migration, then the heliosphere may also be shaped by motion. The sun moves through a changing interstellar medium. If the scattered disk records gravitational scattering, then the heliosphere may record magnetic and plasma scattering. Interfaces in space rarely stay smooth. If the Oort cloud depends on galactic tides and passing stars, then the heliosphere also depends on galactic pressure and local magnetic fields. The farther outward we build, the more the solar system stops looking like a bounded object. It starts looking like a negotiation across scales. In visuals, that negotiation is a set of overlapping fields, gravity fading slowly, debris thinning into statistical fog, and plasma boundaries rippling like a weather front. The same space can belong to the sun in one sense and to the galaxy in another. This is the crucial transition from Chapter 1's hook to the measurement story ahead. NASA expected a clean edge, but our architecture already predicts complexity. The sun's influence never truly ends, but its dominance does. Somewhere, solar wind pressure loses the argument with interstellar pressure. That loss is not a metaphor. It is a measurable change in particle energies, magnetic turbulence, and the balance of forces. We have now built the frontier in objects and in inference. The next step is to follow the probes into the one edge they can directly taste. In the next chapter, the narrative leaves the debris fields and enters the heliosphere itself. The solar system's outer architecture becomes the prelude to a boundary that behaves like a seam. Chapter 2 built the frontier in objects and orbits. Chapter 3 turns that frontier into a physical environment the probes can taste. In the wide shots, space looks like a clean black vacuum, but the sun refuses to leave it empty. It fills the darkness with a moving atmosphere, thin, invisible, and electrically alive. The sun is not only light and gravity, not only a warm disk that holds planets in place. It is a continuous outflow of plasma, magnetic field, and energetic particles that turns interplanetary space into weather. That outflow is the solar wind, mostly protons and electrons with embedded magnetic fields. In plain terms, it is the sun's outer atmosphere escaping, because the corona is too hot to stay bound. The corona reaches temperatures of millions of degrees, and although the gas is extremely tenuous, its particles carry enough thermal energy to expand outward. The expansion is not a gentle breeze, and it is not intermittent like a flare. It is a persistent flow that begins as a pressure-driven escape and becomes a supersonic stream. The solar wind expands outward from the corona and fills interplanetary space, threading between planets and through the asteroid belt. Near the Sun, the wind is accelerated by a combination of pressure gradients and magnetic geometry, and it continues to gain speed as it climbs away. This acceleration is not perfectly smooth, because the corona is structured into open and closed magnetic regions. Open field lines act like exit ramps, and closed loops act like traps that can later break and release plasma. Near Earth, typical solar wind speeds cluster around 400 km per second, with fast streams near 700. Those fast streams often originate from coronal holes, darker patches in extreme ultraviolet images where magnetic fields open outward. Densities are low, often just a few particles per cubic centimetre, yet the flow carries momentum because it never stops. Even a thin stream, moving at hundreds of kilometres per second, can push on magnetic fields and carve boundaries. In plasma physics, speed is not the whole story, because a plasma is also a medium for waves. What matters is whether the wind outruns its own signals, and the solar wind usually does. A gas can carry sound waves, but a magnetized plasma carries additional wave modes that depend on field strength and density. If the flow is faster than those wave speeds, information cannot travel upstream to warn the oncoming wind. The solar wind is supersonic relative to the local sound speed, and often super-alphenic relative to magnetic wave speeds. The alphen speed is set by magnetic tension and mass density, and it acts like a limit for how fast magnetic disturbances propagate. When the wind exceeds it, the magnetic field is dragged outward rather than guiding the flow. That means disturbances cannot travel upstream easily, and the system becomes shock-prone. So the inner heliosphere behaves like a one-way river, even though it is made of charged particles and fields. The Sun sets conditions, and the planets mostly endure them, responding with magnetospheres, auroras, and radiation belts. When the wind changes, Earth does not negotiate with it at the source. Earth only reacts where its own magnetic bubble meets the stream, but the Sun also spins, and that rotation adds a twist that is both geometric and physical. The solar surface rotates roughly once every 27 days as seen from Earth, although different latitudes rotate at different rates. Magnetic field lines are rooted in that rotating surface, at least close to the Sun where the plasma and field are tightly coupled. As the wind streams outward, it stretches those lines into a spiral. This is the Parker spiral, a geometry produced by two motions at once. The wind moves radially outward while the Sun's footpoints rotate beneath it, so the field cannot remain a straight spoke. In diagrams, it looks like a garden sprinkler pattern drawn across the solar system. In reality, it's a living structure that wobbles, folds, and sometimes kinks under changing solar conditions. Close in, the field is more radial, because the wind has not yet travelled far enough for rotation to dominate. Farther out, the spiral tightens and the azimuthal component grows, changing how particles drift and scatter. Charged particles do not simply stream along straight lines, because they gyrate around magnetic fields and bounce off irregularities. The spiral therefore becomes a transport highway, shaping how solar energetic particles spread and how cosmic rays are modulated. The heliosphere is the volume carved by that wind and field, a vast cavity blown into the surrounding interstellar medium. It is a bubble of solar plasma pushing into the galaxy, and it is larger than any planet's orbit by orders of magnitude. If the planets are beads near a lamp, the heliosphere is the lamp's wind-filled room. It is not static because the pressure of the wind changes and the galaxy pushes back. Pressure defines the contest, and in space, pressure comes in several forms that add together. Solar wind dynamic pressure falls with distance, because the wind spreads out like an expanding sphere. Magnetic pressure and thermal pressure also matter, and in the outer heliosphere, pickup ions can dominate the total. External interstellar pressure does not fall the same way, because it is set by the local properties of the galactic environment. At some radius, the outward flow must slow, heat, and compress, because it cannot keep expanding freely forever. The simplest models predict a layered boundary structure, like nested shells around the Sun. Those shells are not walls, and they are not perfectly spherical, but they are useful landmarks for understanding the physics. They are also the landmarks NASA hope to recognize in the data. First comes the termination shock, where the supersonic solar wind is forced to become subsonic. It is a shock in the fluid sense, not a solid barrier, and it forms because the wind must adjust to downstream conditions. In a shock, variables change abruptly over a relatively short distance, and energy is redistributed. The shock is collisionless, meaning particles do not collide like air molecules in a storm front. Instead, electromagnetic fields and collective plasma effects do the work. Across that shock, speed drops and temperature rises because bulk flow energy is converted into random motion. Particle distributions broaden, and turbulence increases as energy is redistributed across many scales. A spacecraft crossing such a region does not feel a jolt, but its instruments see the plasma's character change. The shock's thickness can be comparable to particle gyroradii, not to everyday fluid scales. Beyond the termination shock lies the heliosheath, a thick, disturbed region of slowed solar wind plasma mixed with pickup ions. It is the downstream region of the shock, where the flow is now subsonic and can communicate through waves. Instead of racing outward unchecked, the plasma can respond to pressure gradients and boundary constraints. In imagery, this is the realm of mottled textures and shifting filaments, a place where the wind loses its clean, radial identity. Pickup ions begin as neutral atoms that drift into the heliosphere, often from interstellar space. Because they are neutral, they ignore magnetic fields and can cross deep into solar territory. When they become ionized by ultraviolet sunlight or by collisions, they are suddenly subject to the Lorentz force. They are grabbed by the magnetic field and begin to gyrate, joining the flow with high random energy. That pickup process injects a distinctive population into the solar wind, and it changes the energy budget. A newly ionized particle is not born moving with the wind, so it must be accelerated by the electric fields associated with the flowing plasma. The result is a ring-like velocity distribution that can drive instabilities and generate waves. Those waves, in turn, scatter particles and heat the plasma, creating feedback that simple models miss. Those pickup ions matter because they carry a large fraction of the pressure in the outer heliosphere. They can dominate the shock physics and reshape expectations because they behave less like a thermal fluid and more like a kinetic population. If they absorb much of the energy at the termination shock, the shock can weaken, and the heating of the core solar wind can be reduced. The termination shock then becomes less like a textbook jump, and more like a complicated energy partition. In the heliosheath, the flow is subsonic and diverted, because it must eventually match the boundary conditions at the heliopause. It is heated, compressed, and stirred by instabilities, waves, and magnetic fluctuations that can persist for years. The plasma can eddy and shear, and it can carry the memory of solar events long after they left the inner system. If the inner heliosphere is a river, the heliosheath is an estuary, slower, thicker, and full of mixing. Farther still is the heliopause, the contact boundary where solar plasma pressure balances interstellar plasma pressure. It is the operational edge of the heliosphere, the place where inside becomes outside in NASA's language. It is not the end of the sun's influence because fields and particles can still cross. It is, however, the end of the solar wind as a coherent outward-flowing plasma. In ideal diagrams, the heliopause is a clean surface separating two fluids, drawn like a smooth shell. In reality, it is a region where mixing, reconnection, and draping can occur, and where the boundary can ripple. The solar wind is magnetized, and the interstellar medium is magnetized, so the interface is not purely hydrodynamic. It is a magnetic negotiation, and magnetic boundaries are rarely simple. Outside the heliopause is the local interstellar medium, a thin mixture of plasma, neutral gas, dust, and magnetic field. It is not empty and not uniform, and its properties are inferred as much as they are measured. The Sun is currently moving through a region sometimes called the local interstellar cloud, a patch of slightly denser material within a larger hot cavity. Even in this thin medium, the density and field strength are enough to shape the heliosphere's outer skin. If the Sun moves fast enough relative to that medium, the heliosphere should form a bow shock like a boat's wake. If the motion is gentler, it may form only a bow wave, a compression without a true shock. That distinction depends on whether the interstellar flow is supersonic or super-alphvenic relative to the heliosphere's obstacle. The external magnetic field can soften shocks because magnetic pressure and tension can carry stress without abrupt discontinuities. So even the outermost structure is conditional, and that conditionality is part of the mystery. The edge depends on the galaxy's local weather and the Sun's motion through it, and neither is perfectly known. The heliosphere is a boundary object shaped by two environments at once. It is also an experiment in real time because both environments evolve. This is the first tension point, and it sits beneath the elegance of the textbook picture. The textbook picture looks clean, but the inputs are variable and the plasma is nonlinear. A small change in density or magnetic orientation can produce a large change in boundary behavior. The heliosphere is therefore not only a structure to be mapped, but a system to be interpreted. The sun's output changes with the solar cycle, and those changes propagate outward like a slow heartbeat. Over roughly 11 years, wind speed patterns, magnetic polarity, and energetic particle production shift. The sun's global magnetic field flips polarity near solar maximum, and the heliospheric current sheet becomes more warped. That warp matters because it changes the large-scale magnetic topology that particles experience. Coronal mass ejections add bursts on top of that cycle, and they are among the most dramatic drivers of heliospheric change. They launch magnetized clouds that drive shocks and compressions through the heliosphere, sweeping up slower wind ahead of them. In coronagraph images, a CME appears as a bright, expanding halo, a luminous shell that grows and fades as it races outward. In the plasma, it is a travelling package of field and pressure. Those transients propagate outward for months and years, eventually reaching the heliosheath, where they can merge and pile up. The boundary is therefore driven from inside as well as pressed from outside, and it responds on long-time delays. A spacecraft at the edge is not only sampling local conditions, it is also reading a history of solar activity, stretched across billions of kilometers. The interstellar medium is also structured, and its structure can be subtle but consequential. Density, ionization fraction, and magnetic field direction can vary across small scales, and the heliosphere responds. Even a modest change in external pressure can move the heliopause inward or outward. A tilt in the external field can reshape the heliosphere, making it asymmetric and time variable. So the edge is not a single distance, and that is a crucial conceptual shift. It is a moving balance point, breathing with solar pressure changes and flexing with interstellar pressure changes. It can advance and retreat, and it can do so differently in different directions. The radius of the heliosphere is therefore not a number but a range tied to conditions. NASA expected the edge to be measurable anyway, because boundaries leave signatures that instruments can recognize. Different instruments should agree on the moment conditions change, even if the crossing distance varies. That expectation was not naive, because plasma boundaries often produce multiple correlated shifts. The challenge is that correlation can break when the boundary has thickness, or when different populations respond differently. One signature is particle populations, and this is among the most intuitive diagnostics. Inside, solar wind ions and pickup ions dominate, while outside, interstellar plasma and galactic cosmic rays dominate. A particle detector can measure energy spectra and composition, distinguishing a solar origin distribution from a galactic one. The transition should look like a handoff in ownership from sun-made particles to galaxy-made particles. Another signature is magnetic field behavior, because the heliosphere carries the sun's magnetic imprint. Crossing the heliopause should change the field's orientation, turbulence spectrum, and correlation with solar rotation. Inside, the Parker spiral introduces a preferred direction and a rhythm tied to solar rotation. Outside, the field should reflect the local interstellar direction, draped and compressed around the heliosphere's obstacle. Another signature is plasma density, and density can be inferred even when direct plasma instruments struggle. Interstellar plasma is expected to have a higher density than the hot tenuous heliosheath, and plasma waves can reveal that. When electrons oscillate at the plasma frequency, the frequency depends on density, like a diagnostic tone. A plasma wave instrument can listen for that tone, turning faint electric signals into a density estimate. Another signature is cosmic ray flux, because the heliosphere acts as a modulator and partial shield. Galactic cosmic rays should rise beyond the heliopause as solar modulation weakens, while solar energetic particles should drop. The heliospheric magnetic field scatters and decelerates incoming cosmic rays, reducing their intensity inside. Beyond the boundary, the galaxy's background should reassert itself, and the counts should climb. These are the diagnostics that turn philosophy into measurement, and they are the reason the outer heliosphere is not merely a metaphor. They let NASA define outside without needing a visible wall, and they allow multiple, independent checks. Yet each diagnostic is mediated by plasma physics, and plasma physics is rarely obedient. The same boundary can look different depending on which messenger you ask. But neutral atoms complicate every one of those diagnostics, because neutrals ignore magnetic fields and cross boundaries freely. They carry information across the interface, and they blur the clean separation between solar and interstellar. Interstellar neutral hydrogen can enter deep into the heliosphere, flowing through the Parker spiral as if it were not there. Those neutrals become a hidden interstellar presence inside the Sun's domain. Solar wind ions can steal electrons from neutrals through charge exchange, and that single interaction has outsized consequences. In charge exchange, an ion captures an electron and becomes a neutral, while the original neutral becomes an ion. The newly created ion is then picked up by the magnetic field, joining the plasma with a distinctive energy. The newly created neutral, now fast, can travel freely across field lines. Charge exchange creates energetic neutral atoms, or ENAs, and ENAs are one of the most elegant loopholes in heliospheric exploration. They travel in straight lines, because they are neutral again, and they can be detected remotely. In effect, they are postcards from the boundary, stamped with the energy of the ion that created them. When detectors count ENAs from different directions, they can build a map of distant interactions. This is how NASA can image the boundary without being there, and it is why the heliosphere can be studied as a glowing structure. ENA maps turn the heliosphere into a faint glow of particle interactions, a ghostly outline traced by invisible exchanges. In visual terms, it is like seeing a fog bank not by the fog itself, but by the way headlights scatter through it. The boundary becomes legible through its byproducts. ENAs also drain energy from the plasma, and that drain is not a small correction. When an ion becomes a neutral and escapes, it removes momentum and heat, reshaping shocks and flows. The plasma loses a particle that was carrying energy and pressure, and the neutral carries that energy away without being confined. Over large distances, this energy leakage can alter the thickness of the heliosheath and the strength of the termination shock. So the boundary is not only a hydrodynamic structure, and that is the deeper lesson. It is a coupled system where neutrals and ions constantly trade identities, and where kinetic effects matter. The heliosphere is not a single fluid, because different populations have different histories and different temperatures. Some are cold and newly born, some are hot and accelerated, and some are interstellar visitors. That coupling helps explain why simple models fail, even when they capture the broad picture. Many early models treated the plasma as a single fluid and treated neutrals as a background. Those models produced clean, nested shells, and they were valuable as first approximations, yet they could not easily reproduce the observed role of pickup ions or the energy loss to ENAs. More advanced models add multiple ion populations and kinetic effects, and they simulate charge exchange explicitly. They predict different termination shock distances and different heliosheath thicknesses, depending on assumptions about neutral density and solar wind pressure. They also predict asymmetries tied to the interstellar magnetic field direction. The more physics you add, the less spherical the heliosphere becomes. Even then, the models often assume steady conditions, because time dependence is computationally expensive and conceptually messy. The real heliosphere is driven by time-dependent solar wind and punctuated by transient events, and those events do not average away quickly. A pressure enhancement can travel outward and change the shock location long after it was launched. The boundary is therefore a moving target, and the spacecraft is sampling a snapshot. This is where the documentary's hook returns in technical form, and it sharpens the suspense. NASA expected a clean edge, but the physics predicts a seam. A seam is not a failure of structure, and it is not a vague excuse. A seam is a place where processes overlap, where gradients stretch out, and where signatures can arrive out of sync. A seam has thickness and texture, and that texture can be measured if you know what to look for. It has folds created by changing pressure, and it has patches created by turbulence and reconnection. It can also have layers that are not concentric, because the system is asymmetric. The heliosphere's edge may be more like a coastline than a circle. At the termination shock, the expected transition is sharp in speed but complex in energy, and energy is the hard part. Pickup ions can weaken the shock and spread the change, because they absorb energy differently than the core solar wind. The shock may also be rippled by upstream turbulence and by the arrival of transients. A spacecraft might see multiple crossings, not because it turned around, but because the shock moved. At the heliopause, The expected transition is sharp in composition, but complex in magnetism, and magnetism can deceive. Interstellar fields can drape around the heliosphere and align locally, especially near the stagnation region where flows slow. That draping can make the magnetic field direction look deceptively continuous across the boundary. A clean rotation is not guaranteed, even when the plasma environment has changed. Reconnection can also occur where solar and interstellar fields meet, and reconnection is a powerful rearrangement. It can open pathways for particles and alter how cosmic rays leak inward, changing the boundary's filtering properties. In reconnection, field lines break and rejoin, converting magnetic energy into particle energy. The result can be localized jets, heating, and enhanced transport across what look like a barrier. So the edge can be both a barrier and a filter, and the distinction matters for what reaches the inner solar system. It can block bulk plasma while allowing energetic particles to cross in complicated ways. It can also trap some particles temporarily, then release them when conditions change. The heliosphere is therefore not simply a shield, but a dynamic regulator. NASA's instruments were designed to read these clues, and the design reflects decades of heliophysics experience. Particle detectors count energies and species, separating ions from electrons and distinguishing populations by their spectra. Magnetometers track field strength and direction, looking for shifts in orientation and turbulence. Plasma wave instruments infer density, translating oscillations into numbers that can be compared across regions. The expectation was a coherent story, told by multiple voices that agree on the plot. Termination shock first, then a turbulent heliosheath, then a heliopause with clear signatures. The spacecraft would cross each boundary once, and the data would line up like a checklist. That expectation shaped how teams planned analyses and how they defined success. The tension is that each signature can decouple, and decoupling is where mystery enters. Particles can change before fields do. Fields can change without a clean rotation, and density can jump in unexpected places. Neutral atoms can carry information across the boundary, blurring the timing of changes. A seam can make outside arrive in pieces rather than all at once. Solar cycle timing adds another twist, because the outer heliosphere is a delayed mirror of inner activity. A pressure pulse launched near the Sun can push the termination shock outward, then let it retreat later. That means a spacecraft can meet the shock earlier or later than predicted, depending on the Sun's recent history. Distance becomes a record of time, and the boundary becomes a moving archive. Interstellar conditions add asymmetry, and asymmetry complicates comparisons between spacecraft. If the external magnetic field is tilted, it can squash the heliosphere in one direction and extend it in another. The heliopause may be closer on one flank and farther on another, and the termination shock can be similarly distorted. The heliosphere becomes a three-dimensional object with a lopsided outline, so two spacecraft on different trajectories should not cross at the same distance, and that difference is not a mistake. That is not an error, it is a clue about the heliosphere's shape and about the external field that presses on it. In a sense, the spacecraft become two fingertips touching different parts of the same boundary. Their disagreement can reveal the boundary's geometry. This chapter sets up the measurement surprise without naming it yet, and it does so by tightening the logic. The models predict one kind of transition, but NASA's data will show unexpected structure and timing. The boundary will not behave like a single surface you cross once. It will behave like a dynamic interface you can approach, touch, and sometimes re-enter. The central question sharpens here, because the stakes are conceptual as well as technical. What did NASA actually discover at the edge, and why did the missing simplicity matter as much as the signals? If the boundary is a seam, then every diagnostic must be interpreted with care. The instruments may be correct, while the assumptions about what correct should look like are wrong. Because the heliosphere is not just a boundary in space, and it is not only the Sun's footprint, it is the Sun's negotiation with the galaxy, written in shocks, turbulence, and particle exchange. It is a pressure balance that never fully settles, and a magnetic interface that can rearrange itself. It is also a reminder that even in near vacuum, the universe has texture. And if the nearest cosmic border is this complicated, then every clean diagram is a hypothesis waiting to be tested. The heliosphere becomes a laboratory for collisionless shocks, for multi-fluid coupling, and for the transport of energetic particles. It also becomes a cautionary tale about overconfident boundaries. In space, edges are often regions and regions have stories. Next, we follow the probes into the outer heliosphere where these signatures appear in real telemetry. The seam stops being an idea and becomes a dataset. Chapter 3 described a boundary the probes could taste, defined by particles and fields. Chapter 4 follows the only spacecraft that actually reached it and shows why the edge refused to behave. Voyager 1 and Voyager 2 were built for planets, then repurposed as interstellar sentries. Their gold-plated records and long booms were never meant for this role, yet the mission kept going because the instruments kept speaking. Their trajectories diverged north and south of the ecliptic, turning one mission into 2 experiments. In wide shots, their paths look like twin threads pulled from the same spool, separating into different latitudes as the sun's influence thins. By the outer heliosphere, distance becomes a time delay and a filter for solar history. A pressure pulse launched near the sun can arrive years later, reshaping what the probes meet, like weather reaching a far coast long after the storm. The solar wind is not a steady breeze, but a variable outflow of ionized gas. It carries embedded magnetic fields outward, and it remembers the sun's rotation, so patterns at the edge can trace back to events long forgotten near Earth. The Voyagers do not carry one instrument that declares outside with certainty. They carry a chorus that must be cross-checked, especially after decades of radiation and power loss, when every sensor must earn its authority. Start with the magnetometer, the quiet metronome of the mission. It measures field strength and direction, and it tests whether the sun's spiral yields to the galaxy, one vector at a time. In visuals, the magnetometer boom stretches like a thin antenna into darkness, keeping the sensor away from spacecraft interference. On a plot, the field becomes a line that trembles, then steadies, as if the environment is deciding what it wants to be. The magnetic field matters because it guides charged particles, like rails guiding sparks. A small change in direction can redirect cosmic rays, and a subtle increase in strength can signal compression at a boundary. Then the cosmic ray system, built to count high-energy particles from beyond the planets. It sees galactic cosmic rays rising when solar shielding weakens, and it sees solar particles fading, as if the sun's voice is being drowned out. Cosmic rays are not just numbers on a counter, but messengers with origins and histories. Their energies and compositions reveal how well the heliosphere blocks them, and how easily they diffuse along magnetic field lines. Then the low-energy charged particle instruments tune to the solar wind's energetic tail and pick up ions. They track how the heliosheath fills with heated, slowed populations after the shock, where ordinary fluid rules start to fail. Pickup ions begin as neutral atoms drifting in from interstellar space. Then they become charged by sunlight or charge exchange. Once ionized, they are grabbed by the solar wind's magnetic field and accelerated, creating a population that carries pressure disproportionate to its number. Then the plasma wave instrument, which does not measure bulk flow directly. It listens for electron oscillations, and it turns frequency into plasma density, translating a faint ringing into a physical count. The physics is precise even when the signal is delicate. The plasma frequency depends on electron density, so a higher tone means a denser medium, and that density can distinguish heliosheath plasma from interstellar plasma. One missing voice matters more with every year. Voyager 1's plasma instrument degraded long before the crossing, leaving density to be inferred indirectly, and forcing the team to treat every clue like a witness under cross-examination. Engineers and scientists work around failures by combining partial clues. They compare particle spectra to magnetic context, and they use plasma waves as a proxy for what cannot be sampled, building confidence by overlap rather than certainty. This is where the documentary's central question tightens into procedure. What did NASA actually discover at the edge, and how do you prove it with imperfect sensors, separated by billions of kilometers from the people interpreting them? Even the act of listening is slowed by distance. Radio signals take many hours to reach Earth, so the crossing cannot be experienced in real time, only reconstructed later, like a crime scene assembled from delayed reports. The approach begins with the termination shock, the first major boundary in the textbook diagram. It should be a clear slowdown from supersonic wind to subsonic flow, with heating and compression, like a sonic boom turned inside out. Supersonic here means faster than the relevant wave speeds in the plasma, especially the magnetosonic speed. When the solar wind can no longer outrun its own disturbances, it must adjust abruptly, and a shock is the plasma's way of doing that. Voyager 1 reaches that shock first in late 2004 at about 94 astronomical units. The crossing is not a single clean step because the shock itself moves, pushed and pulled by changing solar wind pressure. In the visuals, the boundary is not a wall but a rippling surface. It advances, retreats and tilts, so the spacecraft can cross it more than once or skim it as it wavers. The data show energetic particles rising upstream, a foreshock region that hints at turbulence and acceleration. The shock looks less like a line and more like a restless surface, where particles bounce and gain energy. Those energetic particles are evidence of collisionless physics. In near-vacuum plasma, particles rarely collide directly, so electromagnetic fields do the work, scattering, reflecting, and energizing ions across invisible gradients. The surprise is not only the shock's character, but its location. Models expected a more symmetric distance, yet the boundary appears closer than many predictions, suggesting the heliosphere is being squeezed. Voyager 2 crosses the termination shock in 2007 at about 84 astronomical units. That 10 AU difference is too large to dismiss as measurement noise and too coherent to ignore as coincidence. 2 spacecraft, 2 distances, 1 sun. The simplest explanation is asymmetry, driven by external interstellar pressure and magnetic field orientation, which can compress one hemisphere more than the other. Time variability also matters, because the solar wind pressure changes with the solar cycle. A weaker wind can pull the shock inward, and a stronger wind can push it outward, so the boundary breathes on multi-year rhythms. The termination shock becomes the first proof that the heliosphere is not a sphere. It is a distorted bubble, breathing with solar output and pressed by the galaxy, and the Voyagers are tracing its shape from the inside. Beyond the shock lies the Heliosheath, predicted to be thick and turbulent, with slowed flow diverted around the heliopause. This is where pickup ions dominate pressure and complicate every fluid assumption, because the plasma is not one simple population. In renderings, the heliosheath looks like a dim ocean of charged particles, threaded by magnetic lines and stirred by instabilities. The spacecraft moves through it like a silent buoy, sampling a medium that cannot be seen directly. Voyager particle instruments see that complication in energy partition. The core solar wind does not heat as much as expected, implying pickup ions absorbed much of the shock energy, leaving the thermal plasma cooler than theory anticipated. That mismatch forces a change in interpretation. The shock is collisionless and multi-population, so a single temperature or speed cannot summarize the physics, and averages can hide the dominant pressures. As the Voyagers move outward, the teams watch for a second boundary signature set. They expect solar particles to drop, galactic cosmic rays to rise, density to increase, and the magnetic field to rotate, like a compass turning as a border is crossed. The tension builds because the signals do not arrive in a tidy bundle. Some variables change abruptly, others drift, and some refuse to confirm the crossing at all, as if the boundary is deliberately out of sync. Voyager 1 enters a puzzling interval in the heliosheath that some call a stagnation region. Flow indicators suggest the outward motion of plasma slows dramatically, as if the river meets a marsh and loses its direction. In that region, the magnetic field strengthens and becomes less noisy, while particle gradients sharpen. The spacecraft seems to approach a boundary that is close yet not declared, like fog thickening before a shoreline appears. Scientists debate whether this is the true edge or a precursor layer. A stagnation region could be a pileup of magnetic flux, or a boundary fold created by pressure changes, and each option implies a different heliopause geometry. The uncertainty is amplified by missing direct plasma measurements on Voyager 1. Without bulk speed and density from a working plasma instrument, the crossing must be inferred from indirect signatures, which makes every disagreement feel consequential. Then the counts change in a way that is hard to fake. In 2012, Voyager 1 sees a sharp drop in solar energetic particles and anomalous cosmic rays, the populations born inside the heliosphere. Anomalous cosmic rays are especially telling because they are made locally. Neutral atoms drift in, become pickup ions, then get accelerated near the termination shock, so their disappearance suggests the acceleration region is now behind the spacecraft. At nearly the same time, galactic cosmic rays jump upward and stay elevated. The cosmic ray system reads it as a new regime, less shielded by the sun, where the galaxy's background becomes the dominant radiation field. This is the signature many expected to be decisive. If the heliopause is the end of solar plasma dominance, the particle ownership should flip, and it appears to with a sharpness that feels like a door closing. But the magnetometer complicates the celebration. The magnetic field direction does not rotate as dramatically as predicted, even as its strength changes, and that missing rotation becomes the mystery's anchor. In the simplest picture, the heliopause should separate the Parker spiral from the local interstellar field. A clear rotation would be the geometric proof of leaving the Sun's domain, like stepping from one current into another. Instead, Voyager 1 measures a field outside that is surprisingly aligned with the inside direction. The boundary looks like a handoff in particles, but not a clean handoff in orientation, and that contradiction forces restraint. That mismatch becomes the core dramatic twist of the chapter. The data say outside and not outside, depending on which instrument you trust, and the mission becomes an argument between reliable witnesses. The plasma wave instrument provides the missing density clue, but only when the medium is disturbed. It detects plasma oscillations triggered by shocks that propagate outward from solar eruptions, turning distant solar violence into a diagnostic tool. Those shocks are like pressure fronts traveling through tenuous plasma, compressing electrons and making them ring. When the wave instrument catches that ringing, it offers a rare moment of clarity, an audible density measurement in a mostly silent region. Those wave events allow a density estimate from the plasma frequency. The inferred densities are higher than typical heliosheath values, consistent with interstellar plasma, and the numbers persist across multiple events rather than a single anomaly. So 3 lines of evidence converge on a crossing. Solar origin particles collapse, galactic cosmic rays surge, and density inferred from waves rises to interstellar-like levels, forming a triangulation that is difficult to dismiss. Yet the magnetic field direction remains stubbornly familiar. That forces new physics into the story, because the instruments are not wrong in the same way, and the boundary must be more subtle than the simplest diagram. One explanation is magnetic draping. As the interstellar field encounters the heliosphere, it can bend and wrap around the obstacle, aligning locally with the heliospheric field near the boundary, like fabric pulled taut around a rounded frame. Draping can make the outside field look like the inside field, even when the plasma environment has changed. The heliopause becomes a geometric trick, not a simple rotation marker, and local measurements can mislead global expectations. Another explanation is boundary geometry and sampling. A spacecraft crosses at one point on a complex surface, and local alignment can occur without global alignment, especially if the heliopause is rippled by instabilities. Reconnection adds a third possibility because it can connect solar and interstellar fields. That connection can allow particles to leak while keeping field directions locally similar, and it can create layered regions where ownership changes before orientation does. The result is a boundary that behaves like an interface, not a wall. It can block bulk flow while allowing energetic particles and field topology to interact across thin layers, so the edge becomes a region with structure rather than a line. Voyager 2 approaches the heliopause with a different instrument set and a different path. Its plasma instrument still functions, giving direct density and speed measurements that Voyager 1 lacks, and making its data feel like a second camera angle. That difference turns Voyager 2 into a crucial cross-check. If Voyager 1's crossing was ambiguous, Voyager 2 can test whether the same signature pattern repeats, and whether the magnetic puzzle is a one-off or a rule. In 2018, Voyager 2 records a heliopause crossing with a similar particle signature. Solar particles drop, galactic cosmic rays rise, and the change persists, indicating the spacecraft is not merely passing through a transient pocket. Voyager 2 also measures a plasma density increase consistent with interstellar values, now with direct plasma data. The plasma wave instrument again supports the density jump, and the agreement between methods tightens the case. The magnetic field behavior remains complicated, though not identical in every detail. The expected dramatic rotation is still muted compared to early textbook expectations, suggesting that draping and geometry are not exceptions but part of the boundary's nature. 2 crossings, 6 years apart, confirm the larger lesson. The heliopause is real, but its diagnostic signatures are not synchronized in the way simple models promised, and the edge refuses to be reduced to a single metric. Now the asymmetry returns with sharper edges. Voyager 1 crosses the heliopause around 121 AU, while Voyager 2 crosses around 119 AU. Despite earlier shock differences that implied a strongly distorted inner boundary, The termination shock distances differed by about 10 AU, implying a compressed hemisphere or a time-shifted boundary. The heliopause distances are closer, implying shape changes with region and pressure balance, and hinting that the heliosheath thickness varies dramatically. That combination suggests a heliosphere that is not a scaled set of concentric shells. The heliosheath thickness and boundary positions vary with direction, time, and external magnetic influence, so the bubble's anatomy changes depending on where you cut it. The heliosphere's shape appears more squashed and asymmetric than many early models assumed. External magnetic pressure and interstellar flow conditions likely play a stronger role than expected, and even small shifts in those conditions can move boundaries by astronomical units. This is where the Voyagers become more than travellers. They become probes of the local interstellar medium, because the outside conditions are what sculpt the bubble, and the bubble's shape is a measurement of its surroundings. Outside, the cosmic ray environment is not simply higher, it is structured. Variations hint that the interstellar medium has its own turbulence and gradients, not a uniform background, and that the heliopause is embedded in a larger dynamic neighbourhood. Inside, the heliosheath is not simply a buffer, it is a mixing zone. Pickup ions, charge exchange, and transient shocks create layers that can mimic or mask a crossing, and they can shift the apparent edge depending on which messenger you follow. Charge exchange is especially deceptive because it swaps identities without changing trajectories. A fast ion can steal an electron from a neutral atom, creating a fast neutral and a slow ion, quietly redistributing energy and momentum across populations. The stagnation hints now read as a warning about definitions. The edge can be approached through a region where flow slows and fields pile up, before the particle ownership fully flips, and before density measurements catch up. So the narrative beat shifts from arrival to interpretation. Crossing is not a single timestamp, because different messengers respond on different scales, and because the boundary itself may be moving while it's being measured. The cosmic ray detectors respond to shielding and transport, which depend on diffusion and magnetic turbulence. The magnetometer responds to topology and draping, which can preserve direction even as the plasma changes. The plasma waves respond only when the medium is made to ring. That dependence on shocks means density is revealed in flashes, moments when the environment is forced to announce itself, rather than a continuous stream of measurements. Even the instrument's aging becomes part of the plot. Power constraints force heaters off, sensors drift, and teams recalibrate with limited options. Yet the patterns persist, and persistence becomes a form of proof. There is also a human history embedded in every plotline. The spacecraft were launched in 1977, and many of the original designers never expected to see this chapter, yet their engineering choices still shape what can be known. NASA expected a clean edge, an ending that multiple instruments would underline together. Instead, the Voyagers report a seam, where some variables jump sharply and others stay ambiguous, like a border drawn in overlapping inks. That seam forces a rethink of heliospheric physics. It demands multi-fluid models, time dependence, and a stronger role for the interstellar magnetic field, because a single fluid, steady-state picture cannot reproduce the observed mismatches. It also changes the meaning of home. The Sun's protective bubble is not a smooth sphere, and its border is not a simple shield line, so the idea of a neat solar territory gives way to a more negotiated boundary. The deeper discovery is not only that the Voyagers reached interstellar space, it is that even here, in our nearest cosmic neighbourhood, the universe refuses clean borders, and it prefers interfaces that blur and shift. The chapter ends with the question sharpened for what comes next. If the heliopause is a shifting interface, what else have we misread about the space just beyond it, and what other boundaries are we simplifying into lines? Next, the story turns outward from the crossing itself to the medium beyond. The Voyagers have stepped into the local interstellar cloud, and the galaxy begins to answer back. Chapter 4 ended with two Voyagers crossing a boundary that would not behave like a wall. The particle counts flipped, densities rose, and the magnetic direction stayed eerily familiar, as if the compass refused to admit it had left home. That mismatch sharpened the central question. What did NASA actually discover at the edge of the solar system, and why did what it did not find matter? Voyager is a point measurement, a fingertip pressed against one location on a moving interface. It tells us what the boundary feels like along a single path, at a single time, with instruments that were never designed for this exact frontier. But a seam can look different from different angles, and local alignment can hide global structure. The heliopause is not a knife-edge surface, and even the word crossing can be misleading when the transition has thickness. To test the shape of the heliosphere, NASA needed a second viewpoint. Not another crossing, but a scan, something that could treat the boundary as a whole object rather than a single encounter. The challenge was brutal in its simplicity. How do you image something that emits almost no light, sits far beyond the planets, and is made of fields and particles? That scan came from a small spacecraft in Earth orbit with an outsized assignment. The Interstellar Boundary Explorer IBEX was built to image the edge indirectly, using particle physics as a kind of night vision. It would not fly to the heliopause, and it would not sample the heliosheath in situ. It would watch the whole sky for a signal that could only be made at the boundary. IBEX is based on a loophole in plasma physics that Chapter 3 introduced. Charged particles are trapped by magnetic fields, so they do not travel straight to a distant detector, even when they carry enormous energy. They spiral around field lines, bounce in magnetic gradients, and scatter in turbulence, motion that looks like wandering rather than pointing. Neutral atoms ignore those fields, so they can cross boundaries and move ballistically. If you can create fast neutrals at the heliosphere's edge, you can detect them at home. Those escaping messengers are energetic neutral atoms, or ENAs. An ENA starts as an ion in a plasma flow, usually a proton moving with the solar wind or the heliosheath, where the wind has been slowed and heated. It meets a neutral atom, often interstellar hydrogen that drifted inward unnoticed because it does not feel magnetic forces. In a charge exchange, the ion steals an electron and becomes neutral, while the neutral becomes an ion. The new neutral keeps almost the same speed and direction as the original ion, because the electron's mass is tiny. That single swap turns an invisible plasma interaction into a detectable particle. The ENA is no longer tied to magnetic field lines, so it travels in a straight line, like a tracer bullet through the dark. Its energy carries a memory of the plasma environment that produced it, including the temperature and bulk flow of the parent ions. Its arrival direction points back toward the region where the exchange occurred, blurred by the fact that the boundary is thick. ENAs turn the heliosphere's edge into a faint all-sky glow. IBEX was designed to count those neutrals and sort them by energy. It spins and its sensors sweep a strip of sky as the spacecraft rotates, building a steady rhythm of sampling. As Earth orbits the Sun, that strip shifts, and the mission builds a full-sphere map over time. The result is not a photograph in visible light, but a particle map, an atlas made from impacts, not photons. The concept sounds straightforward, but the signal is delicate. ENA fluxes are low and backgrounds are real, so the instrument must reject charged particles and spacecraft contamination, including atoms knocked loose by sunlight or impacts. The data must be accumulated over months to build statistically meaningful maps, because each pixel is built from sparse counts. The sky must be separated into energy bands, because different energies trace different parent populations and different regions. IBEX is a slow survey of a fast invisible frontier. There is also a deeper subtlety in what the map means. A detected ENA does not announce a single coordinate in space, because the charge exchange could occur anywhere along a long line of sight through the outer heliosphere. What IBEX measures is an integrated signal, shaped by neutral density, ion density, and the probability of exchange. Even so, patterns can survive integration, especially if the boundary is organized rather than random. NASA expected IBEX to confirm the broad outlines implied by models and by Voyager's local readings. The heliosphere should show a general enhancement toward the nose where the Sun plows into the interstellar flow, compressing plasma and building pressure. It should show weaker emission toward the tail where the heliosphere stretches downstream, thinning and cooling. It should show gradients that reflect pressure balance, pick up ion distributions and solar cycle changes. It should not show a narrow, bright structure cutting across the sky. Then IBEX produced its first all-sky maps, and the boundary answered with something no one predicted. Across the ENA sky appeared a bright, thin arc, like a luminous stitch drawn over a sphere. It was narrow compared to the rest of the emission, and it was sharply defined even after long integration. It looked less like a diffuse glow and more like a seam line. It became known as the IBEX ribbon. The ribbon was shocking because it was not an obvious consequence of the standard picture. Most models produced broad lobes, not a tight band, because they assumed smoother distributions and weaker geometric selection. The ribbon's brightness implied a focused process, not a smooth average. Its geometry implied a relationship to something ordered, not only to turbulence. It suggested that the heliosphere's edge was being shaped by the galaxy's magnetic environment in a more precise way than expected. The ribbon also complicated the meaning of edge in the documentary's hook. NASA went looking for an ending and instead found a seam. IBEX now showed that the seam has stitching, regularity, direction, and an almost architectural coherence. A narrow coherent feature implied that the boundary is not only asymmetric but organised. The heliosphere is not simply pushing into empty space, it is interacting with a structured medium that can imprint patterns across the entire sky. To understand why the ribbon matters, the narration has to pin down what ENA maps actually trace. ENAs detected at Earth were created far away, mostly in the outer heliosphere and near the heliopause, where ions and neutrals overlap. Their energies correspond to parent ions in the Helios heath and related regions, including pickup ions that have been accelerated and redistributed. Their travel times are long enough that the map is time-smeared, carrying solar history with a delay. IBEX is not seeing a static boundary, it is seeing an interface averaged over years. Even with that smoothing, the ribbon stays narrow. That persistence suggests geometry, not a transient flare, because random variations would blur into a wider haze. It implies a preferred direction in space, and the most obvious candidate is the local interstellar magnetic field. The same field that can drape around the heliosphere and confuse Voyager's magnetic rotation signature could also organise ENA production. The ribbon becomes a global clue to the field that Voyager could only sample locally. One leading explanation begins with magnetic alignment. The ribbon appears where the line of sight is nearly perpendicular to the local interstellar magnetic field direction, a condition that can be described as sightlines that see across the field rather than along it. In that geometry, particles can be confined or reflected more effectively, increasing the chance of charge exchange that produces ENAs. The ribbon would then be a map of where the field geometry favours a return signal. It would be less a feature of the solar wind itself, and more a feature of the boundary's magnetic orientation. This idea connects directly to the draping concept from Chapter 4. As the interstellar field encounters the heliosphere, it bends and wraps around the obstacle like fabric pulled tight over a moving hull. Draping can create regions where field lines are compressed and ordered, raising magnetic pressure and reducing cross-field transport. If energetic ions stream along those draped lines, their distribution becomes anisotropic, meaning direction matters. A narrow ribbon could emerge where the draped field geometry concentrates the conditions for ENA creation. Another major explanation is the secondary ENA hypothesis. In this model, the ribbon is not made by primary ions directly becoming ENAs near the heliopause, at least not in one step. Instead, primary ENAs are created in the Helios sheath and fly outward into the local interstellar medium, crossing the heliopause because neutrality grants passage. There, they can be reionized by charge exchange or photoionization, becoming pickup ions outside the heliopause. Those new ions gyrate around the interstellar magnetic field, forming a ring distribution that can be unstable. Then a second charge exchange occurs. Those pickup ions steal electrons from interstellar neutrals and become ENAs again, now launched back inward with a directional bias. Because the pickup ions are organized by the magnetic field, the secondary ENAs are emitted preferentially in certain directions. The ribbon becomes a return echo, an outward message and an inward reply. The heliosphere sends neutrals out, the galaxy converts them into ions, and the boundary sends neutrals back. This secondary process explains why the ribbon could be narrow and bright. It uses the interstellar magnetic field as a focusing mechanism, selecting angles where the ring distribution produces the strongest return. It also explains why the ribbon's location is tied to field direction rather than to the heliosphere's nose alone. It turns the heliopause into a two-way exchange surface, not a one-way boundary. The edge becomes a feedback loop between solar and interstellar populations. A related class of models focuses on magnetic mirroring. Energetic ions approaching a region of stronger magnetic field can be reflected, like particles bouncing in a magnetic bottle, because their pitch angle changes as the field strengthens. If the draped interstellar field strengthens in a band around the heliosphere, ions could be mirrored there. Mirrored ions spend more time in that region, increasing the probability of charge exchange. More time means more ENAs, and more ENAs means a brighter band. Magnetic mirroring is attractive because it links ribbon brightness to field compression, which is exactly what draping predicts near an obstacle. It also resonates with the documentary's theme that the boundary is a negotiation. The galaxy does not merely press on the heliosphere. Its field can trap and redirect particles, shaping where energy is deposited and where signals are returned. The heliosphere's edge becomes a tuned interface, sensitive to external field strength and orientation. None of these models is a simple victory because each must match multiple constraints. The ribbon's width, its energy dependence, its stability over time, and its relation to the broader ENA background all matter. Some models reproduce the geometry but struggle with the intensity, implying missing sources or underestimated efficiencies. Others match intensity but require assumptions about neutral densities or turbulence that are hard to verify. The ribbon is not only a feature to explain, it is a test that forces models to include the galaxy as an active boundary condition. The narration should underline why this is a turning point in the overall story. Voyager told us the edge is confusing up close, where diagnostics decouple and ownership of particles can change before fields do. IBEX tells us the edge is structured at scale, where the whole sky participates and the geometry becomes readable. Together they imply that the heliosphere is not defined only by the sun's output. It is defined by the sun's output meeting a magnetized, partially neutral interstellar environment. IBEX also reframes the earlier expectation of a clean checklist boundary. If ENA emission is organized by external field geometry, then the heliopause cannot be treated as a simple surface with uniform properties. Different longitudes and latitudes will have different coupling to the interstellar medium, because field orientation and neutral penetration vary with direction. Some regions may allow more particle leakage, others may trap and reflect. The boundary becomes patchy in function even if it is continuous in location. That patchiness helps explain why Voyager's magnetic rotation was muted. If the interstellar field is draped, local measurements can align with the Parker spiral direction even outside, producing a deceptive familiarity. If reconnection and mixing create layered regions, particle ownership can flip before field direction does, leaving instruments with contradictory clues. IBEX adds a global context where such alignment is not a surprise, but a geometric consequence. The ribbon is a signature of that geometry made visible. IBEX data also carry time dependence that echoes the solar cycle theme. ENAs detected now were created years earlier, so changes in solar wind pressure and magnetic polarity can appear delayed, like thunder arriving after lightning. The ribbon's intensity can vary with solar conditions, but not instantaneously, because the boundary must be fed by the changing wind. That delay turns the heliosphere into a memory device. The boundary stores solar history and releases it as a changing ENA sky. The ribbon therefore becomes a diagnostic tool for the local interstellar magnetic field direction. By fitting models to the ribbon's position, scientists can infer the field's orientation in our neighbourhood, even though no spacecraft has directly mapped it at large scale. That orientation feeds back into heliosphere shape predictions and into interpretations of Voyager's trajectories. It also ties into broader astrophysical questions, because the local field is part of the galaxy's larger magnetic structure. The edge of the solar system becomes a probe of galactic magnetism. At this point in the chapter, the narration should widen the frame without losing momentum. The heliosphere sits inside the local interstellar cloud, itself embedded in a larger cavity often called the local bubble, and those names carry decades of astronomical inference. That bubble is thought to be carved by ancient supernovae, leaving hot, low-density plasma and complex magnetic topology that still guides charged particles. Our heliosphere is not pushing into a uniform sea. It is moving through a region with history, gradients, and fields shaped by violent events. The phrase local bubble now carries two meanings that can be braided for dramatic effect. The heliosphere is the sun's bubble, carved by solar wind, inflated day by day by a star's continuous outflow. The local bubble is the galaxy's bubble, carved by supernova energy and stellar winds over millions of years. The IBEX ribbon suggests these bubbles interact through magnetic structure. Our smallest boundary is nested inside a larger boundary, and the larger one may be setting the rules. That nesting is the bridge to cosmology that this chapter must set up. If our nearest border is shaped by galactic conditions, then any measurement that assumes a clean local foreground can be biased, especially when signals are faint and backgrounds matter. Cosmic rays entering the inner system are filtered by a boundary tuned by the interstellar field, changing what reaches Earth. Neutral atoms drifting inward carry signatures of the surrounding cloud, including composition and ionization state. Even all-sky backgrounds can be affected by heliospheric emission and scattering. The documentary's larger arc is about borders that refuse to be simple. IBEX shows that the edge is not only messy, but patterned, and patterns imply external control. The Sun is not alone in defining inside. The galaxy participates in drawing the line, and it draws it with magnetism, quiet, invisible, and directional. The ribbon is a visible reminder that space is not empty. It is an environment with orientation. The narration should return to the central question in a compressed beat. What did NASA actually discover at the edge of the solar system? It discovered an interface that can be crossed, mapped, and still not fully defined, because different diagnostics respond to different physics. It discovered that the heliosphere's boundary is responsive to the interstellar magnetic field, and that this field can create coherent global structures. It discovered that the missing clean edge is itself a measurement of our galactic neighbourhood. The ribbon also hints at a deeper methodological lesson. When models fail, the failure can be more informative than agreement, because it exposes which assumptions were invisible. A predicted smooth glow would have been easy to accept and easy to forget. A narrow ribbon forces new physics, and it forces humility about simplifications. It turns the heliosphere into an instrument for sensing the galaxy, not only a shield around the planets. The chapter ends by pivoting outward again. Voyager gave us the crossing, and IBEX gave us the map, and together they set a constraint that the interstellar medium must satisfy. The next step is to ask what kind of interstellar medium can produce both the local confusion and the global ribbon. That means characterizing the local interstellar cloud, its density, ionization, and turbulence, because those properties control charge exchange rates and particle transport. It also means asking what lies beyond it in the local bubble, and how that environment connects to larger cosmic structure. At the farthest border of the Sun's influence, NASA expected a clean edge, an ending. IBEX showed a ribbon in the dark, a bright line where the galaxy touches our bubble, and where geometry selects what returns. The edge is not a wall. It is a seam that glows when particles trade identities, and it glows brightest where magnetism tells them to return. Next, the story follows that magnetism outward into the local interstellar medium itself. The boundary is not the last chapter of the solar system. It is the first chapter of our neighbourhood in the galaxy, and the ribbon is the opening sentence, written in particles and read from Earth. Chapter 5 widened the edge into a ribbon that wraps the whole sky. Chapter 6 steps past the heliopause and asks what the ribbon is actually made of. Interstellar space is not a vacuum with a label that says outside. It is a medium with pressure, fields, dust, and drifting atoms that behave like weather. In wide shots it looks black and still, yet in physics it is a dilute fluid with memory. A few particles per cubic centimetre sounds like nothing, but over astronomical distances it becomes a real atmosphere. The Voyagers crossed a boundary that acted like a seam. That seam exists because two environments press against each other, and pressure is never only one thing. When you add up heat, motion, fields, and fast particles, the balance can shift without warning. The heliopause is where those terms cancel, and where small changes become geometry. Outside the heliopause is the local interstellar medium, the LISM. In our neighbourhood it is dominated by the local interstellar cloud, the LIC. The LIC is not a single wall of material, but a patch of partially ionized gas moving with its own flow. It is the nearest sample of the galaxy's everyday matter, and it is close enough to matter. The LIC is warm by interstellar standards, with temperatures of roughly 5 to 10,000 Kelvin. At those temperatures, hydrogen is not fully stripped, yet it is energetic enough to broaden spectral lines. Visually, imagine a faint warm haze, too thin to see, yet thick enough to push. The gas is closer to a heated plasma-laced fog than a perfect vacuum. It is thin by Earth standards, yet dense enough to matter. Typical particle densities are around a fraction of an atom per cubic centimetre. That means a room-size volume in interstellar space might hold only a few atoms, but a sphere the size of the heliosphere holds an enormous count. Scale turns scarcity into substance. Ionized and neutral components share the same space, but not the same rules. A useful first split is neutral hydrogen and helium versus ionized plasma. Neutrals ignore magnetic fields, while ions and electrons are guided by them. That difference makes the LIC behave like two overlapping fluids that can slip past each other. The LIC is partially ionized, not fully. The neutral fraction and ion fraction vary with radiation fields, charge exchange, and local turbulence. Ultraviolet starlight and hot gas in the broader neighborhood keep some atoms ionized, while recombination quietly rebuilds neutrals. Even a modest shift in radiation can tip the balance. That partial ionization is the first reason small changes matter at the heliopause. Charge exchange couples the two fluids, trading momentum without collisions. An ion can steal an electron from a neutral, and the identities swap in a single encounter. The new neutral flies off with the ion speed, carrying information across field lines. A small increase in neutral density raises charge exchange rates. That can thicken the interface and reshape where pickup ions dominate pressure. Pickup ions begin as neutrals that drift in, then become charged and get grabbed by the solar wind's magnetic field. Once captured, they behave like a new population with extra energy, and they change the heliosheath's pressure budget. A small increase in ion density raises external plasma pressure. That can push the heliopause inward by astronomical units over time. The boundary is not nailed down, because the solar wind itself breathes with the solar cycle. When the sun's output weakens, the outside can win territory, and the seam moves. A small change in temperature changes sound speed and pressure balance. That changes how shocks propagate, and how the heliosheath stores solar history. In a warm, thin plasma, sound speed is high enough that disturbances can spread quickly, yet not so high that shocks vanish. The heliosheath becomes a recording medium, holding the imprint of past solar wind conditions, so the outside is not a static background. It is a set of boundary conditions that can squeeze, tilt, and ripple a solar-scale bubble. In visuals, the heliosphere stops looking like a neat sphere and starts looking like a living membrane. The membrane responds to a changing wind, and the wind itself is structured. Pressure at the edge is a sum of terms that do not announce themselves separately. Thermal pressure, ram pressure from relative motion, magnetic pressure, and energetic particle pressure all compete. Thermal pressure is the simple one, heat in particles, while ram pressure is the shove of bulk flow. Magnetic pressure is stored tension in field lines, and energetic particles act like an invisible gas. The sun moves through the LIC at about tens of kilometers per second. That motion creates an interstellar wind in the sun's frame, and the heliosphere must plow through it. The direction of that wind is inferred from the way neutrals stream inward, like smoke drifting through a doorway. Even when the gas is thin, relative motion gives it bite. The wind is not only gas, it includes dust grains and neutral atoms that can penetrate deep before they are ionized. Some neutrals travel far inside before sunlight or charge exchange flips them into ions. Dust grains, meanwhile, carry mass and charge in a compact form, and they respond differently to fields. This is where the story tightens around a hidden architecture. Magnetic fields are invisible until they bend particle paths, yet they can dominate the pressure budget. A field is not just a direction arrow, because it stores energy and transmits forces. In a plasma, it is both guide rail and elastic band. The local interstellar magnetic field is weak in everyday terms, measured in microgauss. In a tenuous plasma, that is enough to shape global geometry. A refrigerator magnet is unimaginably stronger, yet it acts on dense matter in a small space. Here the field is gentle, but it fills an enormous volume and acts on charged particles everywhere. Magnetic pressure scales with the square of field strength. A modest increase in B can compete with thermal pressure and distort the heliosphere's outline. That scaling is why uncertainty matters, because a small change in field estimate can imply a large change in force. In the outer heliosphere, geometry is a sensitive instrument. Field direction matters as much as strength. A tilted field drapes asymmetrically around an obstacle, compressing one side and relaxing another. The heliosphere is the obstacle, and the LIC is the flow that meets it. If the field arrives at an angle, the drape becomes lopsided, and the boundary becomes uneven. Draping is not a metaphor, it is a measurable consequence of magnetized flow. Field lines pile up and bend around the heliopause, changing local orientation. In a visualization, lines that were straight upstream curve into arcs and tighten near the nose. That tightening is stored magnetic pressure, like a stretched fabric pulled around a moving object. That draping is one reason Voyager did not see a clean magnetic rotation at the crossing. The outside field can look aligned because it is wrapped around the boundary. Instead of a sharp flip, the spacecraft can pass through a region where the field has already been coaxed into a similar direction. The seam hides the contrast by reshaping the field itself. If draping is strong, the heliopause becomes a region of enhanced magnetic pressure. That can explain why the boundary can feel stiff in some diagnostics. A stiff boundary resists motion, so the plasma flow slows and compresses, and energetic particles respond. Even a thin layer can act like a barrier when the field is taut. If draping is turbulent, the heliopause becomes corrugated. That can explain why particle signatures and field signatures decouple in time. A corrugated boundary means the spacecraft can sample folds and ripples, not a single smooth surface. In that case, particles can leak or reflect differently than the field appears to change. The question becomes practical. How do we measure an interstellar field we cannot touch directly when we only sample one point at a time? The Voyagers are needles, not nets, and they traverse a vast boundary slowly, so the field must be inferred with indirect methods, each with its own biases. One method uses starlight polarization. Dust grains align with magnetic fields, and aligned grains polarize passing starlight in a preferred direction. The alignment is subtle, driven by torques from radiation and collisions, yet it leaves a statistical imprint. In the sky, this becomes a faint pattern of vectors, like wind arrows drawn over a map. By mapping polarization angles across the sky, astronomers infer the projected field direction near the Sun. The pattern is faint, but coherent enough to constrain models. It is also local in a useful way, because nearby stars sample nearby dust. The result is not a single line, but a corridor of plausible orientations. Another method uses Faraday rotation in radio signals, where magnetized plasma rotates polarization. It is more powerful at larger distances, yet it anchors field estimates. The amount of rotation depends on electron density and the field component along the line of sight. In practice, it is a long baseline probe that complements local polarization. A third method uses the IBEX ribbon itself as a compass. The ribbon geometry is consistent with sightlines perpendicular to the local field, implying a specific orientation. That perpendicular condition emerges naturally in several models, because particle distributions become enhanced where viewing geometry matches field geometry. The ribbon becomes a sky-wide clue that points back to an unseen direction. These methods do not always agree perfectly. That disagreement is not failure. It is evidence that the local field is structured and the LIC is not uniform. The field can twist with position and density can vary, so different techniques sample different averages. The mismatch becomes a hint that our neighbourhood has texture. Now return to the heliosphere's distortion. Because shape is a measurement, the termination shock distances differed by about 10 AU, implying external pressure is not symmetric. Voyager 1 and Voyager 2 did not encounter the same boundary at the same distance, even after accounting for time variability. That difference is a geometric fingerprint of the outside. External magnetic pressure is a prime suspect. A tilted field can compress the southern or northern hemisphere differently, changing where the shock forms. In a visual, the shock surface becomes an off-center shell, closer on one side and farther on the other. The heliosphere looks less like a bubble and more like a squashed wind-bent sail. Time variability adds another layer. Solar wind pressure changes with the solar cycle, and the boundary responds with delays that can mimic spatial asymmetry. A pressure pulse launch near the Sun can take months to years to reach the outer heliosphere. By the time it arrives, the heliopause may already be responding to a different solar state. The LIC itself may be turbulent. Turbulence changes diffusion of energetic particles, and it changes how cleanly the heliopause can separate populations. In a turbulent medium, field lines wander, and particles scatter more often. That scattering controls how quickly cosmic rays can enter, and how neatly the boundary can act like a filter. Turbulence also changes reconnection likelihood. If interstellar and solar fields reconnect in patches, the boundary becomes porous in selected regions. Reconnection is a topological rearrangement, where field lines break and rejoin, releasing energy and opening transient pathways. It is not a single door, but a shifting set of seams. Porous does not mean open. It means transport depends on energy and pitch angle, and the seam behaves differently for different messengers. high-energy particles can ignore small-scale structure, while lower-energy ions can be trapped or mirrored. The boundary becomes selective, and selectivity is a kind of complexity. That brings the narration to cosmic rays, the most relentless messengers. Galactic cosmic rays are accelerated far away, then diffuse through magnetic turbulence toward us. Supernova remnants and other energetic environments provide the initial push, but the long journey is governed by scattering. By the time they reach the heliosphere, they carry a history written in their spectrum. Inside the heliosphere, the solar wind and its magnetic field modulate cosmic rays. Modulation means the spectrum at Earth is not the spectrum in interstellar space. The solar wind convects particles outward, and magnetic irregularities scatter them, reducing the inward flow. The effect is strongest at lower energies, where particles are easier to deflect. The heliosphere acts like a variable filter. Stronger solar activity increases scattering and convection, reducing lower energy cosmic rays near the inner planets. During quieter solar periods, the filter relaxes and more cosmic rays reach Earth's vicinity. That variability is why cosmic ray detectors on Earth see long-term cycles that track the Sun. At the heliopause, modulation changes sharply. Voyager saw galactic cosmic rays jump and stay higher, while anomalous cosmic rays collapsed. Anomalous cosmic rays are born inside the heliosphere, from pickup ions that get accelerated near the termination shock. When Voyager crossed the boundary, the local source vanished and the galactic background took over. That flip is not only a boundary marker, it is a probe of external conditions, because cosmic ray transport depends on turbulence and field geometry outside. If the outside is calm and ordered, particles can stream more efficiently along field lines. If it is noisy, diffusion dominates and gradients smear out. If the external field is ordered, cosmic rays can stream more efficiently along it. If the field is turbulent, diffusion dominates and gradients become smoother. The difference shows up as how quickly intensities change with distance beyond the heliopause. Voyager's data become a kind of remote sensing, reading conditions it cannot image. Voyager's cosmic ray gradients outside are not perfectly flat. Small variations suggest the LISM has its own structure, not a uniform bath. Those variations can be subtle, yet persistent, hinting at density changes or turbulence changes along the path. Even beyond the heliopause, the environment is not featureless. Some changes correlate with shocks launched from the Sun that propagate outward. Even outside, solar transients can compress the medium and change local particle flux. A shock that begins as a coronal mass ejection can evolve into a broad disturbance by the time it reaches the boundary. When it arrives, it can briefly reshape local pressure and alter particle transport. Those compressions let the plasma wave instrument do its rare trick. It listens for electron oscillations triggered by passing shocks, turning frequency into density. The plasma frequency depends directly on electron density, so a tone in the data becomes a number. It is one of the cleanest measurements Voyager can still make at extreme distance. The measured densities outside are consistent with interstellar plasma, around a few hundredths of an electron per cubic centimeter. The numbers are stable enough to trust. Stability matters because it suggests Voyager is sampling a real ambient medium, not a transient sheath. Even so, small density changes still matter for pressure and wave speeds. Density is not just a number. It sets plasma frequency, alpha speed, and pressure balance, and it controls how quickly disturbances steepen into shocks. Alpha speed depends on both field strength and density, so it governs how information travels along field lines. In plain terms, density helps decide whether the medium responds like a soft fog or a taut elastic network. Density also sets how much neutral gas can survive inward. More plasma means more ionization and more charge exchange, which changes neutral penetration. That penetration matters because neutrals are the raw material for pickup ions and for ENA production. The outside medium therefore influences the inside indirectly through conversion processes. Now the story shifts to the most direct measurements of the outside wind. Neutral helium streams through the heliosphere with minimal deflection. In imagery, it is a quiet river of atoms passing through a magnetic storm, almost indifferent to the fields. Because it stays neutral, it preserves direction information better than charged particles do. Helium is less affected by radiation pressure than hydrogen, and it is less filtered by charge exchange. That makes it a cleaner tracer of LIC flow. Hydrogen feels a stronger push from solar ultraviolet radiation, which can partially cancel gravity and alter trajectories. Helium, heavier and less responsive, keeps a straighter path. Missions like Ulysses and IBEX measured the direction and speed of neutral helium at 1 AU. Those measurements define the interstellar wind vector in the Sun's frame. The instruments effectively watch the sky for an annual pattern, as Earth's orbit changes the apparent arrival direction. From that shifting pattern, the flow speed and direction can be reconstructed. The helium flow is not perfectly constant across decades. Small shifts are debated, and the debate itself signals that the local medium may vary on surprisingly short scales. Are the shifts real changes in the LIC, or subtle instrument and modelling differences? Either way, the uncertainty is instructive, because it tells us how sensitive the inference is. Hydrogen inflow is more complicated. Solar radiation pressure and ionization sculpt it, and charge exchange creates a hydrogen wall near the heliopause. The hydrogen wall is not a solid barrier, but a region where neutrals pile up after losing momentum through charge exchange. In models, it appears as a density enhancement ahead of the heliopause, like a bow wave made of atoms. That hydrogen wall is a density enhancement created by slowed, piled-up neutrals. It is inferred from Lyman alpha absorption and from models constrained by ENA data. Lyman alpha is a resonant ultraviolet line of hydrogen, so even small columns can leave a mark. The wall becomes visible not by glowing, but by blocking and reshaping starlight. Absorption lines are another key tool for the LEC. Nearby stars provide backlights, and the LEC imprints narrow absorption features in ultraviolet spectra. Historically, this technique matured with space-based ultraviolet astronomy, because Earth's atmosphere blocks most UV. Once those spectra became available, the local clouds stopped being hypothetical and became measurable. From those lines, astronomers infer temperature from line widths, and infer column densities from line depths. They also infer ionization state from species ratios. A broader line often means higher temperature or more turbulence, while deeper absorption implies more material along the path. Ratios between neutral and ionized species reveal how strongly the gas is being processed by radiation. Different ions trace different conditions. Neutral species trace cooler, less ionized regions, while ions like Miyutestu and Fe2 trace partially ionized gas. Because each element has its own ionization potential and depletion onto dust, the pattern is nuanced. The LIC becomes a laboratory where chemistry, dust physics, and plasma physics intersect. The LIC is not the only cloud in the neighborhood. Multiple small clouds with slightly different velocities appear in absorption data, implying a complex local flow field. These cloudlets are identified by distinct velocity components in spectra, like overlapping fingerprints. The local interstellar medium starts to resemble a cluster of streams rather than a single uniform wind. That complexity matters because the Sun is moving. Over tens of thousands of years, the heliosphere may enter different cloudlets with different densities and fields. A denser cloud would shrink the heliosphere, while a more rarefied region would let it expand. The boundary we treat as a constant is actually a time-dependent consequence of galactic motion. Even within the LIC, gradients can exist. A small gradient in density or field direction can change the heliopause standoff distance and the ribbon's brightness. IBEX's ribbon depends on where conditions favour ENA production and return, so gradients can tilt the pattern. A gentle change across space can become a bold arc across the sky. Now bring in dust, because dust turns the outside into something you can count. Interstellar dust grains flow through the heliosphere, and some reach the inner system. In visuals, they are tiny meteors without fire, detected only by impacts and electrical signals. Each grain is a solid witness to conditions beyond the heliopause. Dust is charged by sunlight and plasma interactions. Once charged, grains feel the Lorentz force and can be deflected by the heliospheric magnetic field. Photoelectric emission can knock electrons off a grain, leaving it positively charged, while plasma currents can add or remove charge. The charge-to-mass ratio then determines how strongly the grain responds to fields. That deflection depends on grain size and charge. Large grains behave more ballistically, while small grains are filtered and redirected. In effect, the heliosphere acts like a size-selective sieve, letting some grains pass while diverting others. The result is a dust flow that is not identical to the neutral gas flow. Spacecraft dust detectors measured impacts and inferred grain flux and direction. Those measurements show that the heliosphere filters dust, not just cosmic rays. A detector records tiny momentum transfers, sometimes as plasma clouds created on impact. Over time, the statistics reveal a flow direction that can be compared to the helium wind. Dust also ties back to polarization. The same aligned grains that polarize starlight are part of the inflowing population, linking local field direction to local material. Grain alignment is therefore not just an optical trick, but a physical statement about torque, rotation, and magnetic coupling. The field leaves its signature on matter that later enters our system. The outside therefore has multiple components that do not move together. Neutrals stream in, ions are guided by fields, dust is partly filtered, and cosmic rays diffuse. Each component has its own mean free paths and its own response times. The heliopause is where those behaviors overlap, and where the differences become observable. The heliopause is where these components negotiate. It is where charge exchange creates ENAs, where pickup ions are born, and where magnetic draping stores pressure. ENAs are especially cinematic because they travel straight like photons while carrying particle energy. They turn an invisible boundary into a mappable glow, even when it is far beyond any camera. This is the escalation beat. The closer we look, the less empty space becomes, and the more the idea of a simple edge dissolves. A boundary that once sounded like a line becomes a region with thickness, texture, and time dependence. The seam is not a border on a chart, it is a place where physics is busy. The seam is not only thick, it is active. It converts particles between charged and neutral states, and it converts flow energy into heat and turbulence. Every charge exchange event is a tiny transaction that redistributes momentum and energy. Over billions of such events, the boundary becomes a factory for new particle populations. It also acts like a sensor. The heliosphere's size and distortion encode the external magnetic pressure and the external flow, like a windsock for the galaxy. When the outside pushes harder, the bubble shrinks, and when the push is uneven, the bubble tilts. The heliosphere becomes a diagnostic tool, even when we cannot sample the outside directly. So Chapter 6 reframes the Voyagers again. They are not only leaving home, they are sampling the first meters of a much larger ocean. Their instruments are old, yet their measurements are uniquely placed, because no other spacecraft has crossed this seam. The data are sparse, but the implications are wide. Now pivot toward the documentary's central question, because the outside is supposed to be simple. NASA expected interstellar space to look like a clean baseline. The heliopause was imagined as the end of solar influence and the beginning of a steady galactic environment. That expectation was reasonable, because simplicity is how first models survive. Instead, the baseline has texture. The LIC has partial ionization, embedded turbulence, and a magnetic field strong enough to sculpt a solar-scale cavity. The outside is not an inert reference, because it has its own dynamics and its own gradients. The heliosphere is not just expanding into emptiness, it is negotiating with a neighbour. That texture explains why the boundary signatures were unsynchronized. Particles respond to transport and loss processes, while fields respond to draping and reconnection. A cosmic ray detector can register a change before a magnetometer sees a dramatic shift, because particles sample regions differently. The boundary can be crossed in one diagnostic, while still being approached in another. It also explains why IBEX saw a ribbon. A coherent external field and a partially neutral medium can generate a global return signal through secondary ENAs. The ribbon is not merely a pretty arc, but a constraint on geometry and interaction. It is a reminder that the heliosphere is visible, but only through indirect messengers. But the story cannot stop at explanation, because explanation opens a larger mystery. If our immediate interstellar environment can reshape the heliosphere, it can also bias what we think we see beyond it. The heliosphere is not just a shield, it is also a lens that alters incoming particle populations. That lens can imprint patterns we might mistake for distant structure. Foregrounds are not only dust in telescopes, they are plasma processes around our own star. A structured boundary can add emissions and modulate particles that we treat as cosmic background. If we misread the foreground, we misread the map, and the error can look like a discovery. The question becomes uncomfortable. How much of what we infer is shaped at the edge? The heliosphere is nested inside the local bubble, a larger cavity likely carved by ancient supernovae. That larger environment sets radiation fields and magnetic topology. The local bubble's hot, low-density gas helps determine how much ionizing radiation reaches the LIC. Even our local cloud is therefore responding to a bigger stage. If the local bubble is not uniform, then the LEC is not a simple droplet in a smooth void. It is a moving piece of a larger, evolving interstellar landscape. Cloud boundaries, shocks, and magnetic structures can persist for long times, and the sun moves through them. The neighbourhood becomes a dynamic environment, not a static backdrop. Now the suspense turn. We have a bubble shaped by outside pressure, and a ribbon shaped by outside fields, yet we still do not have a clean map of what surrounds us. We infer direction, density, and temperature, but the three-dimensional structure remains elusive. The outside is close, yet it is still mostly unseen. The larger scale structures we infer in the sky depend on subtracting local effects. If local effects are structured, subtraction can create false patterns or erase real ones. A small modelling error at the heliopause can ripple into a large inference about the galaxy. That is why the boundary is not a footnote, it is a warning label. That is the sting in the chapter's final beat. The missing simplicity at the heliopause is not only a local surprise, it is a warning about interpretation. If some expected structures at the edge were missing, like a dramatic field rotation, then other expected structures in our models may be missing too. The universe may be hiding them in interfaces. The LIC is a test case for that idea. It is close enough to probe indirectly, yet complex enough to defeat simple diagrams. Every method, polarization, ENAs, cosmic rays, plasma waves, returns a piece, not a whole. The pieces fit, but they do not lock into a single clean picture. So the chapter ends with a controlled uncertainty. We can estimate density, temperature, ionization, dust flow, and field direction, yet the full three-dimensional structure remains inferred. The uncertainty is not ignorance, it is resolution. Our measurements are still too sparse to turn inference into a map. The boundary keeps its secrets by being extended and active. What NASA found outside was not emptiness, but a medium that pushes back. It was pressure you can balance, fields you can infer, and particles that refuse to respect borders. It was a place where the simplest assumption fails, and where the failure is informative. The outside is not quiet, it is merely subtle. And what NASA did not find was the clean edge that would make outside a simple word. That missing simplicity is the deeper discovery, because it turns home into a negotiation. The heliosphere is not a fortress wall, but a living interface shaped by two winds. We live inside an agreement between the sun and the galaxy. Next, the story asks how far this negotiation extends. If the local cloud can sculpt the heliosphere, what is sculpting the local cloud, and what structures should exist beyond it? Chapter 6 left us outside the heliopause, where outside still had texture and pressure. Chapter 7 widens the lens again, from interstellar weather to the oldest light. The Voyagers and IBEX taught a hard rule about edges. Boundaries are rarely clean lines. Physics stacks layers, and each layer speaks a different dialect to different instruments. A plasma detector reads density and temperature, while a magnetometer reads topology and tension. That rule does not stop at the heliosphere, because the universe has an edge too. It is not a wall in space, but a limit in time and visibility. NASA's most famous map of that limit is not made from stars or galaxies. It is made from a background glow that fills every direction, even where nothing seems to be. On screen, it looks like a mottled sphere wrapped around us, faint reds and blues painted onto a cosmic shell. The cosmic microwave background is the universe's leftover radiation, cooled and stretched by expansion. It is the oldest light we can see directly, because earlier light was trapped. To understand why, the story has to rewind to the first few 100,000 years. The early universe was a furnace of photons, electrons, and nuclei, all colliding in a dense, expanding sea. Temperatures were so high that atoms could not stay intact for long. Electrons and nuclei moved separately, and the cosmos behaved like a bright ionized fog. In plain terms, it was like trying to see through a glowing storm. Photons scattered constantly off free electrons through Thomson scattering, so light could not travel far. Every time a photon tried to move forward, an electron knocked it sideways. The mean free path was tiny, and the universe was effectively opaque. In that era, light existed, but it could not carry an image. Then expansion cooled the universe to a critical threshold, and the balance shifted. Protons and electrons combined into neutral hydrogen, with helium forming as well, in a process called recombination. The name is misleading, because it was the first stable combination on a cosmic scale. What matters is the binding of electrons into atoms, which removed the most efficient scatterers. When electrons became bound, scattering dropped sharply, and transparency arrived quickly. That drop is photon decoupling. Photons stopped being trapped in the plasma and began free streaming through space. The CMB is those photons, released when the universe was about 380,000 years old. We do not see the earlier universe in light because it was opaque. There is a visual way to feel this transition without simplifying it too much. Imagine a fog bank lit from within, then watch it thin until distant shapes suddenly appear. The moment is not instantaneous because recombination takes time across a range of densities. Still, compared with cosmic history, the change is abrupt, an edge in time. Cosmic expansion did not just carry those photons outward as if they were sparks in air. It stretched their wavelengths as space itself expanded, shifting them from visible and infrared into microwaves. The CMB is therefore a cooled afterglow, not a new emission source. Its spectrum is nearly a perfect blackbody, which is a crucial clue. A blackbody spectrum is not just a curve on a graph, because it is a fingerprint of thermal equilibrium. It says the early universe was dense enough and interactive enough to erase memory of how the radiation was first produced. That is why Cobb's result landed like a verdict. If the spectrum had been distorted, the whole early history would have needed rewriting. A simple analogy helps without breaking the physics. The CMB is a baby photo of the universe, taken when it first became transparent. It is not a photograph of galaxies, because galaxies did not exist yet. It is a photograph of conditions, frozen into a radiation field. The first big NASA step was to prove the glow was real and measure it precisely. The cosmic background explorer, Cobb, carried instruments designed for a difficult job, measuring a signal that is everywhere with no off switch. Its Vera's instrument compared the sky to an internal reference, hunting for deviations from a blackbody. It found none that mattered, and the match was astonishingly exact. That success had historical weight, because the CMB itself was discovered earlier by accident. In the 1960s, Penzias and Wilson found an unexplained microwave hiss that would not go away. Cobb turned that hiss into a precision spectrum, and precision changed the field's personality. Cosmology became a measurement science with error bars that could rule models in or out. But a perfect blackbody is only the beginning, because a universe that is perfectly uniform would be simple. It would also be sterile, because structure needs seeds. Seeds require tiny differences in density and temperature, and those differences must survive the early pressure of radiation. The CMB should be almost uniform, but not exactly. Cobb found those tiny anisotropies, and the numbers were almost unsettling. They were at the level of tens of microkelvin on a 2.7 Kelvin background, a contrast of about 1 part in 100,000. That discovery mattered more than the pretty map because it confirmed the seeds existed. It was the first direct glimpse of primordial irregularity. On screen, the map looks like a soft-speckled globe, as if the universe had goosebumps. Yet each speck is a physical statement about density, gravity, and pressure in the young cosmos. These irregularities are not random noise from the instrument. They are the imprint of sound waves in the early plasma, driven by a competition between gravity and radiation pressure. Overdense regions tried to collapse under gravity, and photons pushed back, creating oscillations. The plasma behaved like a coupled fluid, because photons and electrons were locked together by scattering. When a region compressed, it heated slightly and pressure rose. When it expanded, it cooled and pressure fell, and the cycle continued. When decoupling happened, the oscillations froze into patterns, like ripples caught mid-motion. The snapshot preserves phases of those oscillations across different scales. That is why the CMB is not merely a glow, but a record. It is a fossil of a time when the universe rang like a resonant cavity. This is where the documentary shifts from a glow to a code. The anisotropies can be decomposed into angular scales, like breaking music into notes. Cosmologists compute an angular power spectrum, which plots fluctuation strength versus multipole moment. The peaks and troughs are the acoustic signature. Visually, the spectrum rises and falls like a mountain range, and each ridge has a name. The first peak is broad and dominant, and later peaks step down into finer structure. The x-axis is not distance in miles, but angle on the sky. The y-axis is not brightness, but variance, how much the temperature wiggles at that scale. The first peak encodes geometry, because it tells us how a standard physical scale projects onto the sky. That scale is set by the sound horizon. The distance sound waves could travel before decoupling. If space is positively curved, angles appear larger and the peak shifts. If space is negatively curved, angles appear smaller and the peak shifts the other way. A near-flat universe places the peak where flat geometry predicts, and that is what the data show. Flatness here is not a claim that the universe is infinite, because geometry and size are different questions. It is a claim about the rules of triangles on cosmic scales. It says the large-scale curvature is very small, within tight limits. The relative heights of peaks encode composition, and this is where the CMB becomes almost forensic. Ordinary matter interacts with photons and changes the oscillation pattern, while dark matter adds gravity without coupling to light. More baryons boost compressions relative to rarefactions, altering peak ratios. Dark matter changes the timing and depth of gravitational wells. In plain language, baryons make the plasma heavier, so it falls harder into wells, and the peaks respond. Dark matter, invisible to radiation, builds the wells early and holds them steady. Without it, the pattern would not match the observed peak structure. The CMB does not show dark matter directly, but it shows the universe behaving as if dark matter is there. The damping tail at small angular scales encodes diffusion and thickness. Photons random walk before decoupling, smoothing fine structure in a process called silk damping. The finite duration of recombination also blurs small features, because the last scattering surface has thickness. Even the way the spectrum falls carries physical parameters. NASA's next leap was to measure those details with far higher precision. The Wilkinson Microwave Anisotropy Probe, or SMAP, mapped the full sky in multiple microwave bands. Multi-frequency coverage helped separate the CMB from foreground emissions. SMAP turned the power spectrum into a sharp tool. There is a visual rhythm to WMAP's achievement that fits the chapter's mood. The mottled sky becomes cleaner with each data release, and the error bars shrink. The peaks sharpen, and the cosmological model stops being a sketch. It becomes a fitted curve that hugs the data tightly, almost too neatly. With WMAP, the era of precision cosmology arrived, and the numbers began to lock together. The data pinned down a consistent set of parameters that fit a simple model. The universe is about 13.7 to 13.8 billion years old, with uncertainties that became surprisingly small. The geometry is very close to flat. The composition result is the one that changes the story's mood, because it demotes everything familiar. Only about 5% is ordinary matter, the atoms that make stars and people. Roughly a quarter is dark matter, inferred through gravity and required for structure formation. Roughly 70% is dark energy, inferred from expansion history and required for the observed acceleration. The CMB alone does not see dark energy directly at recombination, because dark energy matters most when the universe is older and more diffuse. It infers it through geometry and through how the universe evolved after decoupling. Late-time effects like the integrated SACs, Wolf signal add information on large scales. Combined with other probes, the standard model becomes hard to escape. This is the documentary's escalation beat, because the achievement is both technical and philosophical. NASA mapped the universe with extraordinary success, using a signal that is almost unimaginably faint. Detectors had to be stable, cold, and shielded from stray emission. Calibration had to be relentless, because a microkelvin is a whisper in a storm of systematics. The CMB turned the cosmos into a laboratory, where a few numbers describe everything. It looks like the clean edge we wanted at the heliopause, an elegant boundary that yields to measurement. Yet the story is about edges that refuse to behave. The more precisely we measure the CMB, the more the remaining mismatches matter. Precision reduces random error, but it also exposes systematic cracks. The universe starts to feel less like a solved equation, and more like a controlled mystery. When the best fit model is almost perfect, the leftover residuals become the loudest voice. We begin to ask whether the leftovers are noise or a message. Some tensions are about parameters that disagree across methods. The Hubble constant inferred from the early universe can differ from the value measured in the local universe. The gap is not a single bad measurement that goes away. It persists across improved techniques, and it forces uncomfortable accounting. The amplitude of matter clustering can show smaller discrepancies, depending on the datasets and assumptions. These are not yet definitive contradictions, but they are persistent. They sit in the narrow space between statistical fluke and new physics. That narrow space is where modern cosmology lives. Other tensions are about large-scale features that look odd in a statistically isotropic sky. The quadrupole power is lower than a simple expectation, and some alignments appear unusual. Hemispherical asymmetry has been debated, along with cold spot statistics. Each anomaly alone is fragile, but together they build unease. There is also the problem of missing expected signals at the larger scales. Some correlations appear weaker than predicted on angles above about 60 degrees. Cosmic variance limits certainty on these scales because we only have one sky. Still, the pattern invites the same question the heliopause raised. Are we seeing the universe, or are we seeing our interface with it? At the heliopause, instruments disagreed because the boundary was layered and active. In CMB work, the boundary is not a plasma wall but a foreground problem. We must subtract emissions from our galaxy and from our solar neighbourhood. Foregrounds are not just an inconvenience because they are astrophysics in the way. They are the price of observing from inside a complicated environment. Galactic dust emits and polarizes microwaves, and synchrotron radiation contaminates low frequencies. Even free emission from ionized gas adds structure. On screen, the Milky Way becomes a bright band that must be masked, cut out, or modelled. The clean cosmological sphere is always partially obscured by our own spiral disk. Analysts build templates, compare frequencies, and test how choices affect the final map. The edge of the universe is filtered through the mess of home. The solar system adds its own subtle contributions, and the chapter lingers here for a reason. The heliosphere contains dust, plasma, and energetic particles that can produce faint emissions and scattering. The IBEX ribbon proved our boundary can imprint coherent all-sky structure in particle maps. That does not mean it dominates the CMB, but it warns against complacency. The warning is methodological as much as physical. If a local interface can draw a ribbon across the sky in energetic neutral atoms, then local structure can surprise us in other channels too. CMB teams test for such contamination, and they argue over what is negligible. The debate itself is part of the story, because it shows how hard clean really is. The documentary's premise returns with force. NASA expected a clean edge around the Sun and found a seam. NASA expected clean cosmological simplicity and found a model that fits, yet leaves anomalies and tensions. Both stories hinge on what is missing, not only on what is detected. The CMB is often described as uniform, and that is true in the most important way. It is the same temperature in every direction to high precision, which supports the idea of an early, well-mixed universe. Yet that uniformity is also a puzzle, because distant regions should not have shared information in simple expansion. Inflation was proposed to explain that uniformity by stretching a small region to cosmic size. The same inflation should also seed fluctuations, and it does so in a very specific statistical way. Inflation predicts near-scale invariance and Gaussian statistics with small departures. It can also produce gravitational waves that would leave B-mode polarization. Searching for that signature becomes another edge test. B-modes are difficult because foreground polarization is strong, and the universe does not make the target easy. Dust grains align with magnetic fields and polarize emission, and that signal can mimic the target. The lesson echoes Chapter 6, where dust and fields shaped what we thought was empty space. The universe's oldest light must be read through local magnetism. Even without B-modes, the CMB's polarization carries key information. E-modes confirm the same acoustic physics and Titan parameter constraints. The TE and EE spectra cross-check the temperature spectrum and reduce degeneracies. Every new channel increases precision and also raises the standard for systematics. The power spectrum peaks are the documentary's cleanest example of order at an edge. They show that the early universe behaved like a resonant instrument, with predictable harmonics. Yet the larger scales remain the least tidy, because they are the most limited by our single viewpoint. The edge of observation is built into the data. The edge is the cosmic horizon, and it is easy to misunderstand it as a physical wall. We cannot see beyond the distance light has travelled since the Big Bang, and we cannot see earlier than decoupling in photons. The universe may be larger than the observable region, and it may have structures beyond our horizon. Our map is complete only within a boundary defined by time. This is the parallel to the heliosphere that Chapter 7 needs. The heliopause is a boundary defined by pressure balance and magnetic topology. The cosmic horizon is a boundary defined by causality and expansion. Both are interfaces that shape what can reach us. The narration tightens the mystery because the pattern repeats at different scales. At the heliopause, the missing magnetic rotation forced new ideas like draping and reconnection. In cosmology, missing large-angle correlations and parameter tensions force new ideas about inflation details, dark energy physics, or hidden systematics. The edges refuse to be simple endpoints. NASA's role in this story is not only exploration by travel, because travel has limits. It is exploration by measurement, turning detectors into time machines. COBE and UMAP did not leave Earth orbit, yet they reached farther than Voyager in look-back time. They mapped a boundary that no spacecraft can cross. That contrast is the chapter's pivot. Voyager crosses a seam in space, and CMB missions cross a seam in time. One boundary is local and physical, and the other is cosmic and observational. Both boundaries are defined by what can pass through and what must scatter. Now connect back to the central question without resolving it. What did NASA actually discover at the edge of the solar system? It discovered an interface that behaves like a negotiation, not a wall. Why does what it did not find matter? Because missing simplicity at home trains us to distrust simplicity at larger scales. The CMB is our best evidence that the universe has a coherent story. It gives an age, a geometry, and a composition that fit together across independent measurements. Yet the remaining anomalies sit where the map is most fragile, on the largest scales and at the lowest signals. The universe's edge of observation is where the model is least comfortable, so the chapter ends on a deliberate tension. We have a baby photo of the universe, and we can read its acoustic peaks like a fingerprint. We can infer dark matter and dark energy from patterns in microwaves. Still, some features refuse to behave like a perfectly random, perfectly isotropic sky. The documentary's hook returns in a new register. At the farthest border of the sun's influence, NASA expected a clean edge and found a seam. At the farthest border of observation, NASA expected a clean statistical sky and found hints of structure and absence. The question becomes whether the seams are telling us something fundamental. Next, the story moves from the oldest light to the newest puzzles. If the universe is so well measured, why do its biggest scales still feel unsettled? If our local boundary can shape what enters, what else might be shaping what we think we see? The edge keeps moving, and the mystery keeps its grip. Chapter 7 pushed the edge outward, from Voyager's seam in space to the CMB's seam in time. Chapter 8 delivers the twist, because the shock is not a single object waiting at the frontier. The shock is the missing signature of a clean edge, an absence that refuses to behave like an illustration. NASA went looking for a boundary that would act like a diagram drawn on a whiteboard, a termination shock where the solar wind slows, a heliosheath where it churns, and a heliopause marked by a clear magnetic rotation. Then, beyond it all, a steady interstellar baseline, quiet, stable, and easy to label. That expectation was not naive, and it was not careless optimism from people who should have known better. It was the simplest model that fit early measurements, basic plasma theory, and the way shocks behave in laboratories. When a supersonic flow meets an obstacle, a shock is the standard outcome, because physics prefers abrupt bookkeeping. Voyager and IBEX did find a boundary, but it did not read like a checklist. Particle populations flipped, densities rose, and cosmic rays surged as if a door had opened. Yet the magnetic field refused to rotate like a textbook crossing, and that refusal became the clue. The edge behaved like an interface with thickness, folds, and selective permeability, more like weather than architecture. It looked less like a line you cross once and more like a region you negotiate. In the darkness beyond the planets, the frontier had texture. This chapter is about what NASA did not find, and why that matters more than it sounds. Not finding is not emptiness, and it is not a failure of imagination. Not finding is a constraint that forces models to bend because reality has veto power. In frontier science, absence can be more disruptive than detection because it attacks the assumptions underneath. A detection adds a piece to a puzzle that already has a frame. A null result can break the frame itself, quietly but decisively. Start with the missing bow shock, the one that used to be almost guaranteed in early heliosphere sketches. The sun moves through the local interstellar medium at tens of kilometers per second, carrying its bubble with it. In the sun's frame, that motion becomes an interstellar wind pressing on the heliosphere's nose. Early models treated that wind as supersonic relative to the local plasma, which should create a classic bow shock ahead of the heliosphere. The analogy was irresistible, because it echoes what we see around planets and comets. A fast flow hits an obstacle, compresses, heats, and forms a sharp discontinuity. A bow shock would be a clean signature, and clean signatures are the currency of confident interpretation. It would compress plasma, raise temperatures, and alter particle distributions in predictable ways. It would also define a tidy nose, a clear upstream direction, and a simple outer boundary layer. Visually, you can imagine it as a bright curved shell, like a wave frozen in place, standing off from the heliopause. In simulations, it looks like a crisp arc, with density and pressure jumping across a narrow surface. In a documentary, it would be the perfect line to trace. But the bow shock may not exist, and that single phrase changes the entire mood of the frontier. The data and newer models allow a different outcome, one that feels less dramatic but is more revealing. If the relative flow is subsonic or sub-fast magnetosonic, the plasma does not need to shock. Instead, it can adjust smoothly, forming a bow wave rather than a discontinuity. A bow wave is still a structure, but it is gentler and harder to pin down. The flow bends, pressure rises gradually, and the edge becomes a zone rather than a wall. That difference depends on local interstellar conditions that are hard to measure directly, because we are inside the bubble looking outward. Temperature sets sound speed, and hotter plasma carries pressure waves faster. Magnetic field strength and direction set the Alphen speed, which is the pace of magnetic disturbances through a conducting fluid. Density sets both pressure and characteristic wave speeds, and it also sets how strongly particles collide through collective electromagnetic effects. Small changes in those parameters decide whether a shock can form at all. A modest shift in temperature or field strength can move the system across the threshold. In plasma physics, the threshold is not just supersonic in the ordinary sense. The relevant measure is the fast magnetosonic Mach number, which combines sound speed and magnetic influences. If the flow is slower than that composite wave speed, the plasma can communicate upstream and adjust without breaking. That is why the bow shock was never a guarantee, even if it looked inevitable on early plots. The heliosphere is not a rigid obstacle, and the interstellar medium is not a simple wind tunnel. Both are magnetized, both are partially ionized, and both contain neutrals that ignore magnetic fields until they exchange charge. IBEX and Voyager indirectly tighten those parameters, and the tightening is where the missing signature becomes meaningful. IBEX's ribbon implies an ordered external magnetic field, and order matters because it changes how waves propagate. A stronger or better aligned field can raise the effective magnetosonic speed, making a shock less likely. Voyager's plasma wave measurements constrain electron density outside because plasma oscillation frequencies depend on electron number density. Those faint ringing tones in the data are not just curiosities, they're diagnostics. They turn a distant medium into something you can quantify. Starlight polarization and Faraday rotation add more constraints, because dust grains and radio waves respond to magnetic fields in different ways. Polarization traces the field direction through aligned grains, while Faraday rotation encodes field and density along long sight lines. Together, they narrow the plausible range of field orientation and strength. Put those lines of evidence together, and a strong bow shock becomes less inevitable. The heliosphere may be moving through a medium that's warm enough, magnetized enough, or structured enough to avoid a sharp discontinuity. The missing shock becomes a fingerprint of our local galactic neighborhood. A missing bow shock is not a minor detail that only specialists care about. It changes how the heliosphere couples to the galaxy, because shocks are factories for turbulence. It changes how upstream fluctuations are generated and how they propagate around the bubble. It changes how energetic particles are accelerated and scattered near the nose, because shocks can reflect particles and amplify waves. Without a strong shock, the acceleration environment shifts, and the filtering of cosmic rays changes character. It even changes what we mean by the sun ploughing through interstellar space. Now return to the heliopause itself, where the missing signature is even more unsettling. The expected story was simple, because the ingredients seemed simple. Inside, the solar magnetic field is Parker spiral-shaped, wound by solar rotation, and carried outward by the wind. Outside, the interstellar magnetic field should have its own direction, set by the local galactic environment. Crossing the heliopause should rotate the measured field sharply, because the spacecraft should move from one magnetic domain to another. In the cleanest version, the magnetometer would provide a decisive stamp. Voyager did not deliver that clean rotation, and the absence landed like a quiet contradiction. Voyager 1 saw particle ownership flip in 2012, as solar wind particles dropped and galactic cosmic rays rose. Later, plasma wave detections confirmed an interstellar-like density, reinforcing that the craft was outside, yet the field direction stayed stubbornly similar to the inside, as if the boundary had disguised itself. Voyager 2 repeated the pattern in 2018, again with a muted rotation that resisted the expected narrative. The instruments agreed on outside in particles and density, while the magnetometer refused to cooperate. That absence forces geometry into the center of the story, because magnetic fields are not just arrows in space. They drape, they bend, and they respond to pressure like elastic lines under tension. If the interstellar field drapes around the heliopause, it can locally align with the solar field direction. A spacecraft crossing through a draped region can measure a field that looks familiar even while it is outside. The boundary hides its contrast by reshaping the field itself, an optical illusion made of magnetism. The rotation you expected can be redirected into curvature elsewhere. Reconnection adds another layer, and it is a layer with consequences for mixing. If solar and interstellar fields reconnect in patches, the boundary becomes topologically complex. The crossing becomes less like stepping across a line and more like threading through a braided zone. In reconnection, field lines break and rejoin, allowing plasma populations to exchange pathways. That can produce abrupt changes in particles because particles follow field topology. At the same time, the local field direction can evolve gradually, because the geometry is being reworked rather than replaced. Rippling and time variability complicate the signature further, because the heliopause is not a static shell. It can be corrugated by instabilities, and it can be pushed by pressure pulses from solar activity. The solar cycle modulates the wind, and those changes propagate outward over years. A single spacecraft samples one track through a moving surface, and that is a severe limitation. A delayed or subtle field rotation may occur elsewhere, or at another time, or not at all along that path. The heliopause can be a surface in motion, not a border in stone. This is the limit of single-point crossings, and it is a limit that Voyager cannot escape. Voyager is a needle, not a net, and it cannot map the surface it crosses. It cannot tell whether it passed through a fold, grazed a boundary layer, or crossed a region preconditioned by draping. The missing signature becomes a reminder that the measurement is local while the structure is global. A magnetometer reads what passes over it, not what exists a billion kilometers away. The frontier can be real, and still refuse to look simple. IBEX was built to compensate for that limitation, and its method is elegant but indirect. It images energetic neutral atoms, or ENAs, created when charged particles steal electrons from neutral atoms. The new neutral keeps the original particle's energy and direction, and then it flies straight, unbent by magnetic fields. That straight flight makes ENAs useful messengers, but it also makes them time-smeared. IBEX integrates over long paths and long times, and it depends on charge exchange rates and viewing geometry. It can show a ribbon that wraps the sky, yet still leave ambiguity about the exact mechanism producing it. Visually, the ribbon is haunting, like a luminous seam stitched across the celestial sphere. It is not a point source, and it is not a simple gradient. It is a coherent feature that suggests a coherent field, even as the heliopause itself remains hard to draw. So the heliosphere's edge becomes a case study in how science handles absence. The missing bow shock and missing clean rotation do not mean the models are useless. They mean the models must become conditional, and they must admit parameter ranges instead of single values. They must include geometry, time dependence, and competing processes that can mimic each other in limited data. Draping can imitate continuity, and reconnection can imitate mixing. A boundary layer can imitate a crossing, and a fold can imitate a delay. In practice, absence becomes an upper limit, and upper limits are powerful. If a bow shock is not observed, then the Mach number and external conditions must fall below a threshold. If a sharp magnetic rotation is not observed, then draping, reconnection, or crossing angle must be strong enough to suppress it. Each missing feature narrows the space of plausible worlds, which is what good science is supposed to do. The frontier becomes a sieve for hypotheses, letting some through and catching others. The absence is not a blank, it is a filter. That is the methodological pivot, and it deserves to be said plainly. A detection tells you something exists, and it gives you a target to explain. A null result tells you what cannot be true, at least under the assumed conditions, and that can be more destabilizing. When the null result persists, it can be more valuable than a spectacular object because it forces the theory to move. It forces you to revisit what you treated as background and to ask why the obvious signature is missing. It forces humility into the equations. Now widen the lens again, because the documentary structure demands a parallel. Chapter 7 introduced the cosmic horizon, and it framed it as an edge in observation. We can only see as far as light has travelled, and only back to the last scattering surface in photons. That limit is an edge in measurement, not a wall in space, and the distinction matters. The universe does not end at the horizon, but our direct information does. Beyond it, the cosmos continues while our data becomes inference. The naive expectation is that such an edge yields clean simplicity, because the early universe was hot, dense, and well mixed. The CMB should be statistically isotropic and nearly Gaussian, with correlations that follow the standard model. The power spectrum does fit remarkably well, and that success is real. Yet the larger scales carry tensions and anomalies that feel like missing signatures. They are not loud enough to declare a revolution, but they are persistent enough to keep returning. Like the heliopause, the horizon seems to resist a perfectly tidy story. One missing signature is the lack of large-angle correlation beyond roughly 60 degrees. In a simple model, temperature fluctuations should show a predictable correlation pattern on the biggest angles. The observed sky appears quieter there than expected, as if a piece of the pattern faded. Cosmic variance limits certainty, because we only have one sky to observe. That statistical limitation is itself a kind of horizon, and it complicates interpretation. Still, the absence remains provocative because it sits exactly where the horizon scale should speak most clearly. Other anomalies cluster around alignment and asymmetry, and their very clustering invites suspicion. The quadrupole is low, and some low multipoles appear oddly aligned. Hemispherical power asymmetry has been debated, and the cold spot has been argued over as statistics versus structure. None of these alone overturns the model, and the responsible stance is caution. Together, they echo the heliopause lesson that edges can be where simplicity fails first. If there is a seam in the data, it often shows up at the boundary of what we can cleanly measure. Then there are parameter tensions that behave like absences in disguise. The Hubble constant inferred from early universe fits can disagree with late universe distance ladder measurements. The tension persists across improved datasets and methods, which makes it harder to dismiss as mere noise. It can be framed as a missing consistency, a missing overlap between two ways of measuring the same universe. If both methods are right, something in the model is incomplete. If one is wrong, we must find the hidden systematic that imitates new physics. A similar story appears in matter clustering amplitudes, depending on probes and assumptions. Weak lensing and galaxy clustering can prefer slightly different values than CMB-inferred predictions. The discrepancies are not yet decisive, but they are persistent enough to demand careful accounting. The parallel is not that the heliopause causes cosmological anomalies, and it is not a forced metaphor. The parallel is epistemic, which means it is about how we know what we know. At the heliopause, the boundary is real, but the signature is not clean. In cosmology, the model is broadly successful, but the horizon-scale signatures are not always clean. In both cases, the most important information can be what is missing. The absence becomes the pressure that reshapes the theory. Foregrounds sharpen the parallel, because both frontiers are observed through intervening structure. CMB analysis must subtract the Milky Way's dust and synchrotron emission, and must test how masks and templates change results. The act of cleaning the sky becomes part of the science. The heliosphere is a smaller foreground, but earlier chapters already warned against complacency. A local interface can produce coherent sky structure in ENAs, and coherence can mislead. That fact trains caution about any faint large-scale pattern that seems cosmological by default. Absence also changes how we talk about certainty, and it changes the language of outside. At the heliopause, outside is defined operationally by particle ownership and density, not by a single magnetic flip. In cosmology, the edge is defined operationally by what can be observed, not by a physical boundary. Both edges are interfaces between what we can measure directly and what we infer, and that is where the mystery lives. The frontier is not just far away, it is epistemically thin. It is where data becomes interpretation with fewer safety rails. So what does NASA actually discover at the edge of the solar system, if not the clean border we expected? It discovers that the edge is not an endpoint, and it is not a simple handoff from one medium to another. It is an active negotiation between solar wind pressure, interstellar plasma pressure, magnetic tension, and neutral coupling. It discovers that the clean signatures we expected can be erased by geometry and layered physics. A shock can soften into a wave, and a rotation can hide inside draping. The frontier can be real, and still refuse to announce itself with a single, decisive marker. There is also a historical irony here, because Voyager was launched with one set of expectations and arrived in another era of theory. In the 1970s, the heliosphere was often drawn as a symmetric bubble with a clear nose and tail. Decades of data turned that bubble into a complicated, magnetized interface. And why does what NASA did not find force a rethink rather than a shrug? Because missing simplicity is not a local embarrassment, and it is not a footnote. It is a warning about how humans build boundaries into stories, because boundaries feel like control. We prefer shells, walls, and clear transitions because they are easy to interpret and easy to animate. Nature prefers gradients, interfaces, and regimes where multiple processes overlap. When you reach the frontier, you often find not a line, but a region where rules compete. This is where the chapter raises the stakes for the final act. If the heliosphere does not provide a clean bow shock, then our local interstellar conditions are different than once assumed. If the heliopause does not provide a clean magnetic rotation, then our definition of outside must be plural and instrument-dependent. If the cosmic horizon does not provide perfectly clean large-scale behavior, then our cosmological model may be incomplete even while it is powerful. The universe can be well explained and still not fully understood. The missing signature becomes a way of noticing that difference. The missing signature becomes the documentary's central twist, because it inverts what we expect from exploration. NASA did not find a neat border that ends the solar system's influence like a drawn circle. NASA found an interface that can hide its own contrast, and a universe that can hide its own simplicity. The frontier is not a line, and it is not a final frame where the story stops. The frontier is a seam, stitched by fields, pressures, and particles that trade identities. It is a place where definitions become conditional, and where certainty comes with error bars. End on a bridge to the next chapter's climb, because the seam points forward as much as it points outward. The seam teaches humility as a scientific tool, not as a mood or a posture. Humility means building models that survive ambiguity, and designing missions that can turn single tracks into maps. The next step is to ask what comes after Voyager's point samples, and how we test the missing signatures with new eyes. What would a swarm of probes reveal that a lone craft cannot? And what would a true map do to our favourite explanations? The frontier is asking for a new kind of measurement. The edge of the solar system does not give us closure, and it does not offer a clean ending. It gives us constraints, upper limits, and revised expectations, which is what mature science often looks like. That is the deeper discovery, and it is quietly radical. The universe rarely gives clean borders, even when our diagrams beg for them. It gives measurable mysteries that redefine what we mean by home and outside. And at the seam, where signatures go missing, we learn how much of reality is shaped by what we expected to see. At the farthest border of the sun's influence, NASA expected a clean edge, an ending that would read like a line. Instead, the instruments reported something stranger, a boundary that behaves less like a wall in space and more like a seam in reality. The visuals almost write the expectation for us. A bright spherical bubble surrounds the planets, and beyond it the galaxy begins, dark and indifferent. Yet when the data arrived, the bubble refused to behave like a drawing, and the edge refused to behave like closure. Chapter 8 framed the twist as absence, because the missing clean signatures forced theory to move. Chapter 9 turns that absence into a single escalating idea, because the missing simplicity is itself a physical clue. Boundaries in space are emergent phenomena, built from competing pressures, fields, and statistics. Start with the heliopause, because it is the only edge we have touched directly with a human-made object. It is not a line drawn on a map, and it is not a rigid shell. It is a surface that forms where solar wind momentum and pressure balance the interstellar medium. To make that concrete, picture the solar wind as a supersonic outflow of plasma, carrying magnetic field lines outward like stretched threads. Near Earth it streams at hundreds of kilometers per second, thin but persistent, and it carries energy in bulk flow, heat, and fields. Farther out, it slows, heats, and becomes disordered after the termination shock, where supersonic flow must adjust to the pressure outside. In the simplest picture, that balance creates a stable bubble with a crisp handoff, like air meeting water. Voyager broke that picture, not by failing, but by measuring too honestly across multiple instruments. Particles, fields, and densities did not agree on one clean moment of outside. That disagreement matters because each instrument is sensitive to a different part of the plasma story. Energetic particle detectors respond to populations that can stream along field lines, sometimes far from where they were created. Magnetometers respond to local field direction and strength, which can change smoothly even when particle access changes abruptly. The heliopause is a magneto-hydrodynamic interface, and MHD rarely makes perfect geometric shells. Plasma behaves like a conducting fluid, but the fluid carries magnetic tension that resists bending and snapping. Pressure gradients push, magnetic fields pull, and the surface becomes a negotiated shape. In MHD language, the heliopause is where total pressure balances, not merely thermal pressure. Ram pressure from the solar wind, thermal pressure from heated plasma, and magnetic pressure from field energy all contribute. When any one term changes, the balance point shifts and the surface moves. That negotiation is asymmetric because the interstellar magnetic field is not aligned with the Sun's rotation axis. The external field drapes around the heliosphere, compressing some regions and relaxing others as it flows past. The result is a boundary that is globally coherent but locally deceptive. In imagery, the draping looks like fabric pulled over a moving sphere with folds and stretched arcs. Field lines curve, pile up, and slide around the heliosphere's flanks, and the plasma responds accordingly. Even if the heliopause is one connected surface, it does not promise one simple signature. Voyager's magnetic non-rotation puzzle belongs here, not as an anomaly, but as a lesson in what a boundary can hide. A magnetometer reads local topology, not global ownership, and topology can be misleading at interfaces. If the interstellar field drapes and aligns, the direction can look familiar even after crossing. That is not a trick of wording, it is a consequence of field geometry. Near a boundary, field lines can become tangential, and tangential fields can resemble one another even when they belong to different domains. The crossing can be real, while the compass appears stubbornly unchanged. Reconnection makes the seem more than geometry, because it changes connectivity in a way instruments can disagree about. When solar and interstellar fields reconnect, they create channels where particles can leak and mix across the interface. A particle counter can see a sharp flip while the field direction changes slowly. Reconnection is not merely a cartoon X shape in a textbook diagram. It is a process controlled by microphysics, electron scales, ion scales, and turbulence that ideal MHD can smear out. When reconnection occurs, magnetic energy converts into particle energy, and boundaries become porous without becoming invisible. That porosity helps explain why some populations vanished quickly while others lingered. Galactic cosmic rays can stream inward along newly connected pathways, while heliospheric energetic particles can escape outward. The seam becomes a selective gate, and selectivity is exactly what a clean wall would not allow. Turbulence adds another layer, because the heliosheath is not laminar flow, and never promised to be. Pickup ions, shocks, and pressure pulses inject fluctuations across scales, from large compressions down to kinetic ripples. A boundary embedded in turbulence can be sharp in one diagnostic and fuzzy in another. Pickup ions deserve a brief pause because they are the heliosphere's hidden mass and energy reservoir. Neutral atoms drift in from interstellar space, then become ionized by sunlight or charge exchange, and they are picked up by the solar wind's electromagnetic field. That injection produces non-thermal distributions that carry pressure, drive waves, and reshape the heliosheath's behavior. Time variability is not a footnote, because the sun's output is not steady and never has been. Solar cycle changes propagate outward for years, pushing and relaxing the heliopause like a breathing membrane. A crossing is therefore a snapshot of a moving surface. The time delay is easy to forget when we watch a probe's distance tick upward. What Voyager measures at 120 astronomical units reflects solar conditions from years earlier, carried outward by the wind like weather patterns crossing an ocean. The boundary is not only a place, it is a history. This is why the same boundary can look discontinuous in particle populations and continuous in magnetic vectors. It is also why two Voyagers, on different trajectories and at different times, can tell consistent and conflicting stories at once. The seam is real, but the signature depends on how you touch it. Even the word crossing becomes subtle when the surface itself ripples. A spacecraft can skim a protrusion, then dip back into a fold, and then exit again, all without changing its overall outward path. The data can look like indecision when it is actually structure. IBEX extends the point because it images the boundary without crossing it, and it does so in a different messenger. ENA maps integrate charge exchange events over long paths and long times, turning invisible interactions into sky-wide patterns. The ribbon is coherent, yet it is also a time-smeared projection of a three-dimensional interface. To visualize an energetic neutral atom, imagine a charged ion racing through the heliosheath, then stealing an electron from a neutral atom. In that instant it becomes neutral, no longer trapped by magnetic fields, and it flies straight to the detector like a tiny ballistic report. IBEX collects those reports and reconstructs a map, but the map is an integral, not a photograph. A ribbon that wraps the sky is a reminder that boundaries can write patterns onto our data. It does not prove heliospheric contamination in every channel, and it does not erase cosmological signals by default. It proves that interfaces can produce global structure from local physics. The ribbon also carries geometry in disguise, because its location relates to where viewing directions are perpendicular to the interstellar magnetic field. That perpendicularity condition can create a bright arc even when the underlying plasma is complex. A simple-looking feature can be the projection of a complicated volume. So the heliopause becomes a tangible example of an emergent surface, one we can interrogate with instruments and models. It is shaped by pressure balance, field draping, reconnection, turbulence, and time dependence, all acting at once. It is a seam where the sun negotiates with the galaxy, not a wall where influence stops. Now widen the lens again, because the documentary's structure demands a parallel that raises the stakes. The universe has an edge too, but it is not an edge in space where you could arrive. It is an edge in observation, set by light travel time, expansion, and the physics of transparency. The cosmic horizon is a boundary defined by causality, and causality is not a metaphor here. Beyond it, regions have not had time to send us information since the beginning, because space has been expanding while light travels. The universe may continue, but our direct measurement cannot. When we say horizon, we are describing a limit on communication, not a barrier made of matter. It is the farthest distance from which signals could have reached us in the age of the universe. That makes the horizon a boundary of knowledge, built into space-time itself. The last scattering surface is another boundary, and it is also emergent rather than instantaneous. Recombination and decoupling were not a single moment everywhere, because density variations and finite reaction rates stretch the transition. The CMB comes from a finite thickness in time and space, which blurs fine detail and limits what can be inferred. In visual terms, the CMB is not a flat wallpaper at the edge of a sphere. It is a fog bank that thins, where photons gradually stop scattering and begin to free stream. We see the place where the fog finally becomes transparent, and that place has depth. This is where the word boundary becomes philosophical without leaving physics. At the heliopause, the boundary is a surface with thickness and structure, and its thickness depends on kinetic processes. In cosmology, the boundary is a statistical horizon, where the sample size is one universe. Cosmic variance is the built-in uncertainty of large scales, and it is not a failure of engineering. We cannot rerun the universe to get better statistics, and we cannot observe another sky from another cosmic address. On the largest angles, the error bars are not just instrumental, they are fundamental to the act of observing. That limitation can mimic missing structure, because absence can be statistical rather than physical. A low quadrupole, weak large-angle correlations, and debated alignments can arise from chance in one realization. Yet the same patterns can also be hints of something real beyond our model. The tension is the same tension Voyager created, translated into cosmology, and amplified by scale? Are we seeing a boundary that changes reality, or a boundary that changes what we can know? Does the universe behave differently at the horizon, or do our descriptions fail there? Foregrounds sharpen the dilemma, because every horizon is observed through intervening material and intervening assumptions. The Milky Way's dust and synchrotron emission must be modelled and subtracted, and those models are never neutral. The choices of masks, templates, and priors can move the residuals that look like anomalies. Even with careful analysis, the sky is not a laboratory bench, and the galaxy does not step aside. Dust grains align with magnetic fields and emit polarized light, while relativistic electrons spiral and radiate synchrotron. Each component has its own frequency dependence, and separating them is a test of method. The heliosphere is a smaller foreground, but it is not irrelevant as a warning about interpretation. IBEX showed that our local interface can generate coherent all-sky structure in a different messenger. That lesson forces discipline when we interpret faint, large-scale patterns as cosmological by default. Now connect models to this boundary idea, because model evolution is part of the discovery rather than an afterthought. Early heliosphere models favoured spherical bubbles with neat layers and a possible bow shock, echoing an intuitive picture of motion through a medium. Data forced asymmetry, field draping, neutral coupling, and time dependence into the equations. There is history in that shift because the heliosphere was once imagined with the confidence of limited measurements. As spacecraft explored outward, the solar wind's variability became undeniable, and the interstellar medium stopped being a uniform backdrop. The boundary became a problem of coupled systems, not a single surface. The same arc happened in cosmology, though it looks cleaner from a distance because the plots are smooth. Simple models became parameter-rich precision frameworks, built to fit CMB spectra, lensing, BAO, and supernovae across decades of observation. Precision did not end mystery, it concentrated it into the remaining discrepancies. That concentration is almost cinematic in its irony. The more tightly the model fits most data, the more conspicuous the misfits become, like a single wrong note in a well-tuned chord. Boundaries, once again, are where the wrong notes gather. The Hubble tension is the documentary's clearest example of a boundary between descriptions rather than a single number. Early universe inference from the CMB and late universe distance ladders should meet at one value, if the model is complete and the measurements are clean. When they do not, the gap can be new physics or hidden systematics. What makes it unsettling is that both sides are internally sophisticated. The CMB inference depends on a calibrated sound horizon and the physics of the early plasma, while the distance ladder depends on careful calibration of standard candles and the geometry of expansion. The disagreement is not ignorance, it is conflict between well-built methods. Matter clustering tensions and large-scale anomalies sit in the same uneasy space. They are not decisive revolutions, but they persist across improved datasets and improved pipelines. Like Voyager's muted magnetic rotation, they refuse to vanish on command. So the chapter's central question returns with higher stakes, because the local seam has become a training ground. What did NASA actually discover at the edge of the solar system? It discovered that the edge is an interface where diagnostics decouple, and where missing simplicity becomes a measurable constraint. And why does what NASA did not find matter? Because not finding a clean wall at home trains us to distrust clean walls in our cosmological stories. It suggests that many edges are not endings, but places where competing processes overlap. This is the emotional crescendo, and it must stay grounded in testable claims rather than mood. Humans crave clean borders because they promise closure, and closure feels like safety. Science replaces walls with questions that can be measured, and the most unsettling questions are the ones that survive measurement. So what would it take to test competing interpretations of the heliopore's seam instead of debating it as a metaphor? First, better ENA imaging, with higher sensitivity, broader energy coverage, and faster cadence that can track change. If the ribbon is a secondary ENA echo, time delays and energy dependence should match specific geometries. Those time delays are not abstract, because ENAs carry travel times like timestamps. Higher energy neutrals arrive sooner, lower energy neutrals arrive later, and the differences can encode distances to the emitting regions. A mission that resolves those delays can turn the ribbon into a ranging experiment. If the ribbon is a field perpendicular viewing effect, its location should track the external magnetic field direction with predictable stability. If magnetic mirroring dominates, The intensity pattern should respond to changes in turbulence and pitch angle scattering. A sharper map can discriminate mechanisms that look identical in coarse data. Second, better MHD and kinetic hybrid models that treat neutrals pick up ions and turbulence self-consistently. Ideal MHD can hide the microphysics that sets reconnection rates and boundary thickness, and that thickness affects what a spacecraft samples. Improved models must predict not just shapes, but the instrument-level signatures Voyager actually measured. That means predicting what a detector counts, not only what a simulation displays. It means forward modelling the distribution functions of particles, the anisotropies created by magnetic geometry, and the transient pulses driven by solar variability. A seam is not understood until the measurements are reproduced in detail. Third, multi-point boundary crossings, because single tracks cannot map a moving surface with folds. A swarm of small probes could sample different latitudes and longitudes, turning a one-dimensional story into a three-dimensional one. Time-separated crossings could separate spatial structure from temporal motion. In the mind's eye, the swarm becomes a constellation of needles touching a fabric. One probe crosses where the seam bulges outward, another where it dips inward, and a third where turbulence frays the interface. The boundary stops being a guess and becomes a mapped object. An interstellar probe concept makes the test explicit, because it is designed for the seam rather than stumbling upon it. A faster craft on a chosen trajectory could cross the termination shock and heliopause with modern instruments and modern telemetry. With plasma, fields, energetic particles and neutral sensors working together, the seam could be characterized rather than inferred. Those missions also test the Sun's galactic environment, because the heliosphere is a sensor for the local interstellar medium. Density, temperature, ionization, and magnetic direction outside set the boundary conditions, and boundary conditions decide the shape. Measuring them directly turns the heliopause from a mystery into a calibrated interface. Now mirror the future tests in cosmology, because horizons also have competing interpretations that can be challenged. Next-generation CMB surveys will map temperature and polarization with lower noise and better foreground separation, and they will do it across more frequencies. They will test whether large-scale anomalies persist across frequencies, masks, and analysis pipelines. Polarization is especially valuable because it encodes different systematics than temperature. Dust and synchrotron polarize strongly, yet their spectral behavior can be measured and separated with enough bands. If an anomaly survives that gauntlet, it becomes harder to dismiss as foreground bookkeeping. Large-scale structure surveys add a different handle on the same universe, and they probe different epochs. Bohr provides a standard ruler, weak lensing traces mass directly, and redshift space distortions probe growth over time. Cross-checks between CMB inference, BAO distances, and supernova ladders can isolate where the model breaks. If the Hubble tension is systematic, improved calibration and independent ladders should converge as uncertainties shrink. If it is new physics, the fix should leave fingerprints elsewhere, in early universe sound horizons or late-time growth patterns. The horizon becomes a laboratory for consistency. Cosmic variance remains, but techniques can work around it in limited and clever ways. Multiple traces can reduce sample variance in some measurements, because different galaxies can sample the same underlying modes differently. Better sky coverage and polarization data can test whether anomalies are artifacts of foreground handling. The point is not that every mystery will resolve cleanly, because clean endings are not promised by nature. The point is that boundaries can be interrogated, even when they are not walls, and even when they are statistical. The heliopause can be mapped as a dynamic surface. The cosmic horizon can be constrained as a limit on information. Now the philosophical question tightens, because the chapter is the climax, and the analogy must land. If boundaries are emergent, then reality does not change at a line like a switch. What changes is which interactions dominate and which information can cross. At the heliopause, charged particles are guided by fields, while neutrals cross almost freely until they exchange charge. At the cosmic horizon, photons carry information only from the last scattering surface, while gravitational effects can hint at what lies beyond. Each boundary is a filter, not a stop sign. That framing makes the seam metaphor precise rather than poetic, and it keeps it accountable to physics. A seam is where two regimes meet and exchange stress, and stress leaves measurable signatures. It is where the stitching holds, and where it can fray under load. NASA's deeper discovery is therefore not a single measurement at 121 AU, dramatic as that number sounds. It is a pattern across scales, where edges become interfaces, and interfaces become limits of certainty. The universe rarely gives clean borders, only measurable mysteries that reshape what we mean by home and outside, end by setting up the final chapter's resolution without dissolving the tension, because the story is not finished. The edge of the solar system is not where space ends, and it is not where the narrative should stop. It is where certainty starts to thin, and where better measurement becomes the only honest way forward. Chapter 10 will ask what it means to live inside nested horizons, from heliopause to cosmic background. It will return to the carrier wave still arriving from deep space, and treat it as a message about method. The seam does not close the story. The seam opens it. We asked what NASA found at the solar system's edge, and the answer is a seam, thin, shifting, and surprisingly alive in the data. After decades of flight, Voyager's instruments watched the solar wind fade, then measured an asymmetric, time-variable heliopause shaped by external magnetic fields and interstellar pressure. On the plots, particles flipped ownership as energetic ions dropped and galactic cosmic rays surged, while plasma densities rose as if a new medium had been entered. Yet magnetic direction stayed deceptively familiar through draping, ripples, and reconnection, like a fabric pulled taut over a moving frame. What NASA did not find was simpler and more disruptive. There was no clean border, no single signature, and no final diagram that closes the story, only a crossing that looked different depending on time and angle. That absence tightened physics, constraining bow shocks, Mach numbers, and local cloud conditions, and forcing models to match what the antennas actually heard. Now widen the lens. Cosmology repeats the lesson, with extraordinary order and irreducible limits set by horizons and variants, where even perfect maps end in uncertainty. Science advances at interfaces, where expectations fail and measurement begins. The Voyagers continue outward, carrying a message from a species still learning. The edge is real, not a wall but a doorway. Out past the last planet, NASA expected a diagram, a clean sequence of shocks and shells, a border you could draw with a ruler. Instead, Voyager and IBEX delivered a contradiction that kept repeating, the farther we went, the solar system's edge behaved like weather, not architecture. The termination shock arrived early for one probe and late for another. The heliosheath thickened and thinned, and the heliopause refused to announce itself with one obedient unanimous signature. Particles, fields, and densities told overlapping stories that would not perfectly align, as if the boundary itself were layered, folded, and alive. Galactic cosmic rays rose, solar particles collapsed, and plasma wave measurements whispered higher densities, yet the magnetic field often kept a familiar direction, draped and bent like fabric pulled tight across an unseen frame. IBEX then widened the mystery into a global image, a bright ribbon wrapped around the sky, hinting that an external magnetic field was not just present, but in control. Step by step, the chapters forced the same conclusion. The sun does not end in a wall, it negotiates through an interface, shaped by turbulence, pressure, neutral atoms, and reconnection that can turn a single crossing into a deceptive moment. And the deeper revelation was negative, the missing simplicity, the absent bow shock, the absent clean rotation, the absent textbook certainty, became a measurement that constrained our neighborhood, telling us the local interstellar medium is warmer, magnetized, structured, and strong enough to sculpt the heliosphere's very geometry. When we widened the lens to cosmology, the lesson held, because the universe also hides its truths in seams, where foregrounds, variants, and interfaces can masquerade as fundamental signals. The edge of the solar system became a warning and a tool, a leaky filter that modulates what reaches Earth, and a reminder that even our cleanest maps may carry the fingerprints of the boundary we live inside. The heliosphere's missing expected structure was not a failure of instruments, it was a failure of the assumption that nature prefers crisp borders. The termination shock was real but mobile and asymmetric. The heliosheath was real but uneven and turbulent, and the heliopause was real but not a single surface. More like a region where ownership of particles and pressures trades hands. The magnetic field non-rotation puzzle did not mean Voyager never left. It meant the field outside can align with the field inside, draping and reconnecting until a dramatic turn is no longer guaranteed. In that sense, the probes did not simply cross a line. They moved through a topology, where geometry and timing decide which instrument sees the truth first. The missing bow shock sharpened the picture even more, implying the sun's motion through our local cloud may be fast magnetosonic, producing a bow wave rather than a shock, and forcing models to match specific temperatures, densities, and field strengths. The IBEX ribbon, persistent and narrow, suggests that our bubble is tuned by an ordered external field, and that the outside is not empty space, but a medium with direction, texture, and memory. Yet the 3D map remains incomplete, because 2 Voyagers are still only 2 needles through a vast fabric, and the ribbon is an image made from neutral echoes that smear time into every pixel. That unresolved geometry is not a loose end by accident. It is the next measurement frontier, demanding more trajectories, more viewpoints, and a true cartography of the sun, galaxy boundary. And that is where the story loops back into the oldest light, because we learn to fear the comforting word background. If the heliosphere can imprint structure on particles, fields, and faint emissions, then every all-sky measurement must ask a harder question. Are we seeing the universe, or our interface with it? The cosmic microwave background sits at the edge of time, but it reaches us through layers of local complexity, from the Milky Way to the heliosphere's own subtle contributions, and the discipline of cosmology lives or dies on how well we subtract the near to understand the far. Voyager's lesson does not claim that CMB tensions and anomalies are heliospheric illusions. It claims something more unsettling, that interfaces are where models break and where hidden systematics can hide in plain sight. The same kind of missing signature that ruled out a bow shock can also, in principle, rule out cosmological stories that lean too heavily on idealized skies. In both cases, the absence is not emptiness. It is information, a constraint that reshapes what counts as evidence and what counts as outside. For decades, we treated the solar system like a kingdom with a border, and the galaxy like a backdrop. But the boundary we reached is neither. It is a living contact zone where the sun's breath meets interstellar pressure, where neutral atoms trade charge and become messengers, where cosmic rays are filtered and redirected, and where magnetic fields can slide past each other, reconnect and rearrange the rules. The edge is plural, the edge is moving, and the edge depends on how you ask the question. That is the thread that tied every chapter together, from the outer architecture of icy bodies, to the plasma physics of shocks, to the ribbon that wraps the sky, to the local cloud beyond, and finally to the cosmic horizon itself. We went looking for an ending, and what we found was a method. Measure the seam, constrain the unseen, and accept that the universe offers interfaces before it offers answers. Call back to the opening question is unavoidable, because the hook promised a wall and delivered a seam. What did NASA actually discover at the edge of the solar system, and what terrifying absence forces us to rethink our place in the universe? NASA discovered that the solar system does not end, it transitions through a shifting asymmetric interface where the sun and the galaxy continuously renegotiate the boundary conditions of our existence. And the terrifying absence was not a monster in the dark, it was the missing clean border, the missing bow shock, the missing magnetic rotation, the missing simplicity, because it means home is not enclosed by certainty, but buffered by a dynamic filter whose shape is set by forces beyond the sun. So our place in the universe is not defined by a line we can cross and forget. It is defined by a membrane we live inside, one that changes with the solar cycle, with interstellar weather, and with the magnetized currents of our galactic neighborhood. The Voyagers did not just travel outward. They revealed that the word outside is a model-dependent claim, and that reality often refuses to match the cleanest diagram in the textbook. At the edge of the sun's empire, NASA found an interface, and in that interface we glimpse a rule that scales upward, from heliopause to horizon. Borders are where the universe hides its complexity, and where our certainty is most likely to fail. If you want to see what comes next, follow the missions that will turn 2 crossings into a map, because the seam is still there, and it is still speaking. NASA didn't hit a wall, it entered a negotiation zone, where particles flip allegiance, densities rise, and magnetic fields drape and reconnect instead of cleanly turning. What NASA didn't find, a crisp border, a bow shock, a single definitive signature, forces us to admit that outside is not a place, it is a changing set of conditions. In the end, the edge of the solar system is not where the sun stops, it is where certainty stops, and measurement begins. The universe rarely grants clean borders, only measurable mysteries, and the seam we call home may be the first one we truly learn to read. Listen for the next signals, and support the next generation of heliosphere mapping missions, because the boundary that shaped us is still unfolding.